All right, what's up, everybody? Welcome to Jupiter Brain. Today, we have a very special guest. I can't wait. I'm so pumped for this. Anjali, we've been trying to get you on here forever now. And
since the beginning.
Yeah, Anjali is such a busy and elusive woman, apparently. But anyway, so Anjali is, for one, she is an officer of Physics Society, and we're going to talk about Physics Society here in just a second because we got some great news this morning. And then, two, you're an engineering physics major, right? You're in your third year, right?
Fourth year.
Fourth year, okay.
Well, technically, yeah, fourth year.
Okay.
A junior. Next year I'll be a senior.
Okay, nice, nice.
Cool.
And then me and you started doing research with Dr. Lamachani the same time. We both took his modern physics course, and I feel like we've been friends ever since. Yeah. So I remember the fondest memory I have of you, Anjali, is when we went to APS Dallas. And, I wasn't sure how it was going to go. This was the first time me and Anjali were going to be together for a long period of time because we were riding together down to Dallas.
I bummed a ride off you.
Yeah. Yep. And Anjali talked the whole time. And I was honestly really surprised, but super stoked. Because I was surprised because you're sort of a quiet person, I would say. And then, but whenever, you get stuck in a car for 3 hours, then you can just go on.
I have a captive audience. I like captive audience.
So yeah, ever since that, I was like, okay, Anjali's dope. And I've been trying to get you on the podcast ever since. Well, I guess we started the podcast a little bit after that, but,
Yeah.
Whatever. But anyways, so yeah, I just want to sing some praises for you at the moment because I just think you're a badass, right?
Yep. She gets shit done.
Yeah, I mean you've been working so hard on your research for the last 2 years. You've gone to a lot of the conference I have. You've just stuck with it. Where some people fall off. We've seen, right? But you've stuck with it. You seem to be a really good student. You're a leader in the lab, right? You're a leader in Physics Society. And
she's also one of the hardest workers in maintenance.
Yeah. Okay. Yeah.
Because
Nice.
we both work on campus.
Of course. But yeah. So I just want to say thank you for being a badass, Anjali. You've made my life easier.
I'm glad. That was my goal.
But yeah. So some good news, right? I don't know. Do you want to tell?
Well, today we got the announcement that we have sponsorship funding of $500 for the engineering banquet.
Heck yeah.
UCOSA granted our request for Physics Society. So that was great because I didn't think we were going to get the whole amount that we requested, but
True.
they really supported.
So will you go into sort of the background of how this all started and who's asking us to sort of get money for the engineering banquet and also that you're on the board of the engineering banquet? Can you go into a little bit of the background?
Yeah. So the engineering department this year, the engineering banquet, which is an annual gathering celebration of all the engineering students, they asked for all the student clubs to lead the planning and the whole event. Well, not the whole event, just a collaboration. But all the clubs are asked to donate some money for the catering, and the awards are made by the students for the students. The award descriptions, we came up with those.
Okay.
It was really fun.
Yeah, I'm excited to hear those. The last year's were pretty interesting.
Yeah.
Last year's there's there's serious awards and there's also the silly ones. And for Physics Society, we're kind of a new club. So there are 7 engineering clubs total. I'll try to list them off, BSME, ASME, the BRC, IEEE, SPS, and I think 2 others.
There's like 7 of them, right?
Yeah.
Yeah, so I know you keep saying that we're kind of a new club, but I feel like we've been around for a while. Because I remember, so whenever I first started going to school here, about 3.5 years ago, right? You know, Dr. Teo was one of the first people that I talked to whenever I got here. And he, ever since I've been here, has been doing this bi-weekly seminar where someone gives a talk on their research or a topic that they're interested in. So that part of it has been going on for a while. Dr. Teo has been keeping that sort of alive for a while now.
Yeah.
And then, you know, he had sort of asked/told me that there needs to be, you know, a student president and somebody needs to take the reins on this thing and actually like try to build it up a little bit more. And so I finally did that after I think a year and a half of being here, and just saying, okay, screw it, let's do it. And then of course I asked my closest friends, hey, do you want to help me with this thing, you know? And
you
so
hop on?
Yeah, so Anjali was one of the first to say heck yes to that. And so, you know, I don't know. So it wasn't last semester we started, and I believe it was the semester before that. Is it a year or a year and a half that we've been running this bad boy?
I think it's a year and a half.
Yeah.
It's like in the spring, maybe we started.
Yeah, I think
Last spring.
maybe was it last spring or the fall before that? So 2024 fall. I think it was the fall of 2024. I think so. Because I think that's when we went to AP Dallas, right?
Yeah.
Were we? I don't know. Anyways.
Yeah, so many things have happened.
Yeah. Life's been so busy. So you know, I would say we are new-ish, but we're mature.
Yeah.
You know, like we've this year or this semester we have raised what about. Well, now over $1,000, right?
Yeah.
Basically $1,300, something like that.
Yep.
And hopefully more.
Hopefully more.
Do you want to talk about what you're trying to get money for?
Oh yeah. We're hoping to get money so that students can build their own cloud chamber for particle physics experiments. And for those who don't know what's a cloud chamber, it's just a very cold cryogenic chamber that cools alcohol enough to what's it called? To form condensation whenever there's ions that travel through. Yeah. So we plan to use that to demonstrate particle physics, electrical science, and also solid state physics. And we plan to demonstrate that both in UCO and in schools around Edmond.
Yeah, and I think it gives us some on hands, you know, like building things, right? We want to do more engineering type projects.
And it's pretty affordable. Yeah. It's like the cheapest ones I've seen, the cheapest builds is like $65 per cloud chamber. Yeah. That's about like maybe the size of this bottle. Yeah. Slightly bigger.
So we're going to be asking, I think we put in for $650.
Yeah.
So if we get that, right? Yep. Which it's sort of the end of the semester and it doesn't seem like there's very many clubs asking for money. So
and they will try to give away everything.
Yeah, exactly. So I think as long as we go in there and kill it, which I'm sure you and Albert are going to, because I'll be gone next week, and so you guys
our president will be in Virginia.
Yeah. At Anchor, right?
Anchor, yeah. I forget exactly what it stands for, but essentially
National Conference of Undergrad Research.
Okay, there we go. I was wondering what that C was. I was like,
conference.
I guess that makes sense, right? Yep. Man, so yeah, I'm just super stoked, right? It seems like the ball is finally rolling downhill, and we're not having to keep pushing it uphill.
We're starting to pick up momentum as well.
Yeah, and we're starting to get a real feel for how to get money, right? Because really that's what it all
we want to do.
Yeah, that's what this all comes down to, right? Is if we want to be a successful club, we need money to do these things.
Oh yeah.
And so I'm really hoping. Well, yeah, you guys should get the yearly funding next semester, right?
Yeah, the budget was put in, so
yeah.
Budget's gonna.
Yeah, so we need to make sure to keep putting that in.
Yep.
But yeah, so busy, right?
Yeah. Came a long way.
Yeah. So I know Anjali wanted to talk about biomimicry today, which I haven't got to look into it too much this morning. I definitely had. I always like Friday morning is like or Friday is like my podcast day. So I'm like Friday morning I'll wake up and I just like start reading on the topic diving into it. I typically will throughout the week try to read some things and stuff, but some weeks are just super busy. But I was amazed at the variety of ideas and topics, and it gets into material science. It gets into all different sorts of things,
tissue engineering, all kinds of stuff.
But so that's what we're going to try to talk about today. But first, Anjali, how was your week?
Oh, yeah. I like this question. Honestly, it's a whole memory test. My week's been going pretty well.
Okay.
Does everyone else blink out when they ask that?
Oh, yeah. A lot of people that be like, oh, good question.
Well, for Albert, it's so hard getting him to talk about himself. He likes talking about science and let's talk about science.
I just don't remember. I don't even remember what I did last night. Yeah. So you asked me what I did the whole week. I did not remember.
Oh, jeez. Well, we know Wednesday. No, never mind. Last Wednesday, I guess, is when we asked for the money, right?
And this Monday, you guys have a meetup, right?
Oh, yeah, we met we had a meeting this Monday.
For the Cloud Chamber?
We were putting in money. We put in the sponsorship request Monday.
Yeah, for the project. And we talked about the t-shirts, because we're planning on giving away t-shirts for everyone involved in Physics Society. So faculty, students, officers.
Oh, exciting.
Hopefully give away some during the engineering banquet.
Mm-hmm.
Yeah.
That would be awesome.
And also to the elementary school when we go visit them.
Yeah, as long as we get them in time, we'll be able to give them out. It may be something where we don't get them until after the semester, and then we just hold them until next semester, and you guys hand them out then. Something like that. So did you have a bunch of homework this week, or?
It's been a lot of projects.
Okay.
Just today for fluid mechanics, our team finished our report, and so I'm done with that lab. So that was great. This past week, the nanoparticle research that Dr. Tej has me, Tom, and Daniel working on. Matthew, Tom, and I, the research group.
Yep.
We were meeting up, talking about the glove box, and there's a call from WhatsApp. I don't know where that's coming from.
You can silence it or something.
Yeah, I think they'll message me.
Okay. Yeah, anyway.
It's probably a scam.
Yeah, we're a scam.
So,
trying to get some money from you.
They're like the sponsorship funding.
Yeah.
Oh no. But yeah, the nanoparticles were closer to making them, but I need after this meeting, I'm going back to the lab to work on that.
Okay.
Yeah.
I'll be heading over there with you.
Yeah.
Yeah. I got to work on my mechatronics project.
Yeah, dope.
Our trash can is super close.
I saw the trail on the ground.
So yeah, I totally scrapped that idea. So
now it's just RC.
Yeah. So with those little IR sensors, you need about 5 of them in order to follow a line pretty well.
Oh.
I got you.
Yeah.
Okay.
And so instead of putting 5 of those things on there, because it would just kind of get crowded and stuff, I was like, okay, I'm scrapping that and just going to the idea that I wanted to do in the beginning, which was be able to. Well, it's not really machine learning. It's
path memory.
Path memory, yeah, which is really more simple than what it sounds like. So the basics is you want these motors for the wheels that have encoders built into them. So essentially, they give you data about how much the wheels spin, right? How much the left spins, how much the right spins in its path, right? So that you can just reverse that and then it'll go back to where it came from, right? So I actually set up a a website. Right, so I can Wi-Fi into the ESP32 board and control the trash can from my phone.
Oh, that's dope.
Yeah,
That's
going to a specific
controller.
IP address. Yeah.
My phone is now the controller for my robot.
Yeah.
That's awesome.
Yeah, so literally I was just like, you have it go forward, right, left, or backwards, right? And then before you start moving the robot, what you do is you press record path, and then you go the path you want to go. And then once it's at the destination, you say, okay, stop, basically like stop recording, and then save path, and then you can hit go home, and it'll go
Backwards.
back in reverse. Yeah,
That's insane.
Goodness.
yeah. So it's like it's still a little. It doesn't like at the moment it goes forward, and it'll go back. But it doesn't take turns, and it doesn't remember the turns at the moment. So that's going to be a little bit more coding to do.
Yeah.
But that should be just about it.
Wow.
Yeah.
You're already there.
Almost.
I can't wait till the trial period where you'll have trash and it'll just like take it.
Yeah. It's,
Wait, so I'm curious. So, do you want to briefly explain why you guys are making nanoparticles?
Nanoparticles. Well, this is like one of those closed research things that Dr. Ted said can't talk about it. But I think like there's already papers out on it. So like what we're trying to do is we're making cobalt nanoparticles, and we're making this solution of that, and then we're adding an amino acid, histidine. And what happens is the histidine bonds to the cobalt in a way where it attaches to the side of the particle, and when you shine polarized light onto it, the CD scan will tell you what kind of light is being attached. If it's like left-hand polarized light, which I'm kind of iffy on the details.
chirality.
Chirality, yep.
It shows the chirality of the molecule.
Because amino acids are chiral.
Interesting. Isn't that what's weird, right? It's like there's molecules and certain particles, right, that are chiral or are left-handed or right-handed.
All major, not all, but most major macromolecules, right? Like nucleic acids, amino acids, and carbs are chiral.
So is it just like, okay, so there's if you sum up all of the particles in our body and molecules or whatever, and if the overall sum of them is left versus right, then is that why we're left-handed or right-handed?
No, that's completely different.
Okay.
So if I'm not mistaken, all carbs are right-handed, right? And all carbs and
Are you saying I'm a carb?
no. So basically, so it's pretty arbitrary. It's just that it's a naming convention that we say, that's right-handed. But all nucleic acids are left-handed. That's why DNA only coils one way. It doesn't coil the other way.
Yeah, I see.
Yeah. So they bend light in a specific way too.
I see.
Because of that chirality.
So you don't have to say what it actually is, but like what mechanism or part of this research is Tej wanting to say hush hush about? Is it the elements you're using
The
or
applications.
Oh, okay, that's
medical
fine.
Applications.
Yeah,
Okay,
that's fine.
I
That's
see.
fine. Yeah.
interesting?
understandable.
And this is through the OK Embry
Yeah.
grant, right?
Yeah. Okay. Embry with OU.
We love OK Embry. We love funding.
Heck
Anyways.
Yeah. So interesting. So you were mixing chemicals together yesterday. Can you?
Yeah.
What were you doing that for?
It's to make the cobalt nanoparticle solution, and it's cobalt chloride, sodium citrate, the histidine, and what I'm doing is the dihistidine, which is the right-hand version. And that's the one that's actually harmful. Like, if you have dihistidine, it's toxic.
Yeah.
It's hazardous to the body. L-histidine is the one that's natural, or like
Yeah.
the one in nature.
Let me
Naturally produced.
yeah.
Interesting.
And I think you have to engineer the dihistidine version because that's not the natural one. But it's the same composition, just the right-hand version. And so I'm mixing that solution, and it has to go to the microfuge and like be rotated so it
the centrifuge
becomes Well, it's a microfuge because it's just smaller.
Oh, okay. That makes sense.
Okay, so I got it the other way around. So sugars and DNA is right-handed, and amino acids are left-handed.
Okay.
In natural, like in every life on Earth.
Wow.
In every life on Earth. Almost. I guess we haven't really found every, but in every life we found, this is the same, because like what she said, if there's like right-handed amino acids, for example, it will like ruin protein folding, for example, if they use.
But isn't that weird though? Was like, you know, a human can be left-handed or right-handed, right? Because we have two hands, but molecules don't have two hands.
Oh, it's more like it's more like you can look up chirality of molecules.
Okay. Here we go.
Anything 3D can be chiral. Anything that has a 3D structure can be chiral.
I see.
So,
you said chirality of what?
Of organic compounds.
The crazy thing is how light. I didn't know light had two different like polarizations or main ones.
So there's circular, and then there's linear, and then there's elliptical too.
Ooh.
Elliptical is just a type of circular is a type of elliptical.
Centricity is equal to 0.
Is this kind of like what it's?
Yeah. So if you look at that, you look at that one.
Which, this one?
Yeah, this one.
Oh, okay.
And depending on the kind of light that absorbs, you can tell what its chirality
Exactly.
is.
So they interact with light slightly differently because they are charged. Their charge comes from the fact that some of the atoms are more electronegative than others.
Yeah.
So light interacts with it slightly differently.
You think it'd be R-alanine and L-alanine?
No, I agree. I don't understand.
Right
but
left.
there's a reason for that. No, I remember they named it D for a reason. Why right-handed is D?
I actually do not know.
Interesting. So and then dextro.
It just means it just indicates that something is clockwise if rotation when polarized light is given off.
Oh. Okay, interesting.
Yep. Anyway,
dextro sounds like dextrose.
Yep.
Anyways, so tell me about this machine that Tej has been talking about a lot lately.
The thin film system.
Yeah. Have you gotten to look much into it?
We've uncovered the box, and we're planning to move it to the STEM lab into the clean room. It has better ventilation. It's a thin film magnetron sputtering system, and I do not know the details. So
okay.
Yeah,
let's
sputtering is like spewing particles onto encoding. Like
okay.
that.
What?
thin film sputtering.
Magnetron sputtering.
Magnetron sputtering.
Yeah.
That makes it sound much cooler.
It does.
Everything in STEM sounds cool.
What is the film magnetron sputtering machine? Oh, whoa. Sputtering machine is a high-tech spray painter used at the atomic level. It is a type of physical vapor deposition system that allows scientists and engineers to deposit incredibly thin, uniform layers of materials ranging from a few nanometers to several micrometers onto a surface. Okay.
It's gonna coat our materials.
Yeah, I see. And this will have something to do more with your other research, right? Which is
the electroplating iron cobalt boron with tantalum.
Yeah.
And so for that, we're trying to make a chip, like the materials for a chip. And we'd have silicon. We'd coat that with tantalum, which is a rare earth element. It has like high thermal resistance, corrosion resistance. So that would be good in like high heat applications when there's a lot of heat in the chip system. And after tantalum, we would coat it with iron cobalt, which would be magnetic. and then boron, which helps stabilize that magnetism. And we do layers of that. So it'd be tantalum, iron, cobalt, boron, tantalum. And once you build a lot of layers, the material will become like hybridized. It combines all the properties of each of those layers.
Wow.
So we're trying to make a new material like that. And it requires, like, we're doing electrodeposition currently, and that's the cheap method. You have your redox reaction where electrons are being transferred between the metals. Like, imagine a beaker. We have an electrolyte solution.
I can pull it up, Anjali.
Yeah, a diagram.
That would be good.
You said
Good for
the redox reaction?
Yeah. In Chem 2, they do redox reactions.
put
Electrodeposition.
electrodeposition.
That would be.
Electro.
It's like electroplating, sort of, right?
Yes. Doesn't require much power.
Yeah, kind
We're
of
giving
this, right? I like
current
this.
and voltage through potentiostat, which Sean is supplying.
Yeah, which tells you tells you what about the solution? Tells you how much.
It tells you the rate of deposition in the solution.
Okay.
And every time I talk about it, there's just so much chemistry. I don't know.
The rate of deposition. So how much the material is clinging on to the thing it needs to.
Yeah, and it also is plotting the current and voltage that's being discharged into the beaker and into like the metals that we're giving.
Yeah.
So the setup that we're doing is a 3-electrode setup. Our working metal is silicon. The reference electrode is graphite rod, or counter electrode is graphite rods, and the reference electrode is silver wire. And so we're giving current and voltage through the silver wire, and it's connected to the silicon, and it's giving power for the reaction to start, for electrons to be transferred, and for our solution, the metals in the solution, to be plated onto.
Hello, space travelers. Want to look sharp while bending space-time? We've got brand new Physics Society t-shirts. The clean graphic tee is just $20, and if you want to drop some Einstein-level wisdom on the back with this quote, "I have no special talents, I am only passionately curious," that one's only $25. Rep your curiosity, rep the cosmos, and support the Physics Society. Grab yours today before entropy takes over.
The silicon.
So how does this you said potentiostat, right, is what it is? How does it know how much is being deposited onto this thing? I mean, I'm guessing you're, in some way it's seeing less of the particles that are being deposited onto something, but then those particles are still in the solution, right? So
It's measuring the current and voltage going through the electrodes, and when there's less voltage that's being able to go through, it knows there's more things coating it, like giving resistance.
Yeah. That makes sense.
That's the general explanation that I can give.
Yeah.
And also,
because that's all I understand.
You don't know the quantum mechanics, Anjali, of it?
I don't know the behavior. There's like metal reduction potentials and adding, like there's additives like citric acid that reduce the potential so you can plate easier. Like the reaction will happen easier.
Interesting.
And
so how many projects are you on? Just the 2 or?
3.
Okay.
There's also the magnetic sustainability review.
Oh,
But
yeah.
I want to write and like research well on that, and I just don't have the time. And winter break, I did other things.
Yeah.
My personal.
Yeah. Sometimes you gotta take a break.
yeah, it makes sense.
So I thought Levi had.
He's working on it too, but he's also like been publishing his ANSYS simulations.
Yeah.
He's been working really hard. Like
Okay.
he would be. He's got a lot of things he can talk about that.
Okay.
But he's finished another one, I think, an ANSYS simulation for a paper Dr. Tej needed it for. And he's also like Aiden's joined the research group as well
That's what I heard.
to learn ANSYS with him. So,
Yeah.
We are the 2 like co-authors on that magnet sustainability review. But I also think it probably needs to be opened up for more people. So that way it'll be more likely to be finished.
Yeah, and so I know that Tej, tried to get us all on that, but for me, it's definitely hard. I've got so much going on, but that would be a good, like, your first project coming on to into our research group, right? It's sort of like a literature review, which is what labs typically have you do in the beginning is a literature review, right? So you get a good idea of what's all happening in the field. So, I think it would be a really good task for somebody who's interested in getting into research and getting to see all the different ways people are trying to be sustainable. And then it's also what we're trying to do, right? Try to build sustainable magnets.
Yeah.
So yeah.
Use what we have in the U.S., which is when Dr. Tej told us this, like the U.S. has a lot of cerium, and that's why we're trying to make magnets with it. So because we don't have as much of the other rare earth elements, and I thought that was amazing, and I was like, yeah, sustainable magnets. That sounds great.
Resourceful.
Yeah, but the more I dive into it, it's like, well, this is really tough to build a cerium magnet because of the electron configuration of cerium, and that's one of the reasons why it's so hard to predict for magnetism in cerium compounds.
It's not as strong.
Yeah, and you have a lot of these quantum, what they call the Kondo effect, right? Which things are moving.
Electron effect.
Yeah. That just make sort of looking at cerium hard. But that's also one of the interesting things about looking into cerium is that there's all of these interesting properties and things going on with it that make it a challenge, but kind of an interesting challenge.
Weird quantum behavior.
Yeah, exactly.
One of those.
But yeah, that's what's kind of interesting about our research group, right? Is like we have quite a bit of people now, right? It started off with 3 of us, me, you, Jeff.
4 of us.
4.
Yeah, Jace, Jeffrey.
Oh yeah, that's right, Jace. Yeah.
And I was like, everyone has a J in their name somewhere, like Dr. Ted.
Yeah.
Anjali.
Yeah.
And now the next group that joined us was Matthew, Levi, Haley, and I think.
Yeah, where the J's at?
Yeah, I was like, there's no J's. There's the new generation.
Yeah, but it's interesting because it's like you start to see, because we have so much equipment now, we're able to do a lot more, but then now it's like, okay, I wonder how many people Tej is like realistically wanting to get in our group, because it just seems to grow every semester. And we were talking with Dr. Waters, and she said, she said she had 10? How many research did she say she had under her? And she was like saying I was about to go crazy. Maybe it was 7 or 8.
It was not a lot. It was not that many. It's less than 10 for sure.
Yeah, it was like 6, 7, or 8, something like that. And
there's 2 numbers. I hope it was.
I think it was. Man, I don't know. I can't remember. That was one number I had stuck with me for a long time.
It's just a handful. It's not a lot. So it's just a handful. What I'm thinking is Dr. Tej is looking for whoever is productive and whoever is not productive, and he's gonna he knows that those who are not productive will naturally get laid off, because they'll naturally be too busy to quit. So I think because he just started his lab, he's trying to get as many students as possible. Whatever has potential, whatever is productive, whatever's enjoying it will naturally stay. Whatever isn't will naturally get left behind.
For sure.
The job it rules out.
So he knows he doesn't have to fire anyone, because he knows that people will naturally drop it if it's too tough.
And then especially since we're not we weren't getting paid in the beginning anyways, so so that leads me into a question, Anjali. So what made you stick around and stick with it?
You're one of the few people that actually stuck to Dr. Tej's lab, that didn't actually give up or shows up all the time.
And I get this a lot because just talking to other engineers and stuff, and they, how would I say, I don't know. I guess they just have this idea about Tej that I think is like totally off. They think that he's like too hard on people and expecting too much out of you. But I honestly think that's a great
He sees the best of you, right?
Yeah. But anyway,
Yeah.
but so what's made you stick around?
Well, I want experience, and like I don't think a job's gonna be easy. So if it's hard now, I think that's just gonna benefit me a lot more than later. And like they say, like when you make mistakes now, you're learning. You're in a good environment. This is the time to make mistakes as you want.
Yeah.
I say that, but also like need to do better in my classes and studying. So, but I also think the way Dr. Tej, like how he makes his exams, how he teaches, I enjoy how the rigor that he puts in it. Like I don't always get to the standard that he's asking for. Like I think in our engineering optics class, Levi has been excelling.
Okay.
If you ask him, like, we get homework assigned, and then I ask him about it, or like he asks me, like, hey, what'd you think about the homework? I'm like, I haven't started yet. And he's like, I've already finished. And the way he says it is so funny.
Yeah.
But like, I enjoy his tests because they go into the math, they go into the concepts, and he asks like questions that really make you think, like, what do I think about this? How do I answer that? And it's because of the math, I think, that his classes are more hard. But for research, like...
'Cause he's so good at math.
Yeah.
He's so good at math.
Every physics professor, every equation, they know it, it's all in their head. Everything connects and makes sense. They don't have to look at something for reference. I want to get to that level someday.
Yeah, Tej will just come up with things on the spot. Like he doesn't really know where something's coming from, and then he'll just you'll find him. We'll just be in class, and he'll just like, let me think about this for a second, and he just goes and he'll be silent for like a minute or two, and then just out of nowhere he's like, oh yeah, and then just.
That's insane. Yeah. I've never taken his class, but that sounds crazy.
And that's like in a modern physics course where we're learning these like hard quantum mechanical ideas.
Too.
Yeah.
Like it is mostly a lot of geometry, so it makes sense. Like he goes back, he thinks about it, and he's like, okay, that's not right, or like I missed to account for this bit. And research, I find his explanations like he understands it's all difficult. Like this is all new information. And he like really gets it. I think the reason I joined in the first place was because he said he was starting up a lab. Like if he didn't say this was a whole new lab that he was starting up, I don't know if I would have joined. At least not like as soon as I did in sophomore year, because I was new to research when I joined. So, and also it felt like a thing for juniors and seniors, and actually they don't let freshmen do research. So at least that's what I've heard, because it's only like sophomores, juniors, seniors. So that was very inviting. And my principle is like I just want to learn, get experience, and if I stick with it, then I will eventually get better. So that's what I've tried to do. And I don't know about you guys, but what reassures me is like if I can be a warm body, aka if I don't know anything mental wise, at least I can physically be there.
Yeah.
To do the things. Yeah. And that's just how I approach it.
Yeah.
Oh, that's cool.
And being that warm body, sometimes things rub off. You know?
Yeah.
and I think you can't be afraid of like super smart people, because Tej is like one of those people that could easily how I want to say, like sort of put some people off, or not, that's not the right word, intimidate you because he's so knowledgeable, right? But and sometimes even I think, oh, this is a dumb question, but I ask it anyways. And Tej is sometimes he will give you like, you should know this kind of look, but he'll answer it anyway.
Yeah, he likes questions. Like he was very enthusiastic in modern physics. Yeah, and I in the end of years or end of semester review, I was like, your passion and your enthusiasm is so great. Like I really enjoyed having this class. And when at the end of the semester, when he was like, we can't do the nuclear physics topics because it's time for finals, but he was like, does anyone want to learn? I would actually be down, rather than studying for finals. I want to hear about that.
Yeah. But me and Anjali were like the only people in that class who were like, yeah, let's go.
It was cool. And yeah, he knows so much. He's got a lot of experience from Intel and all the universities that he's been. I don't know his bio as much as I should, but.
Yeah, and I was worried about this at first, right? I was worried that there was going to be too much of a language barrier between me and Tej. Because, his first language is not English, right? And so, I was worried. I was like, I've had professors before that their English wasn't great. And sometimes I struggled in the class, right? But so... and just telling myself, like, well, look at it as like a challenge, right? And look at it as, well, you're going to go to industry, you're going to go to maybe another college or whatever. You're going to end up being in situations like this. So you might as well get used to it. And, it was one of the semesters where I read the textbook more than ever. Just to make sure that, whenever he would say words that I wasn't familiar with, in his sort of broken English, right, I would get it right away. And then you just come to find that Tej is like one of the nicest and kindest and chill human beings ever. Yeah.
Okay. One of his descriptions in engineering optics was like talking about solar fields in New Mexico, I think. And he said like New Mexico, I believe, is one of the shiniest places on Earth. And they exploit it for solar power. And I was like, gotta write that down. I was like, that is the best description I've heard. I love it.
The shiniest places.
Yeah.
High albedo.
Yeah.
He calls it shiniest. It's crazy.
Yeah. And also, like, for our textbook for optics, it's like the author's name is this guy, it's Pedroti, this lady, Pedroti, and then there's another name that's Pedroti. And he was like, Father Pedroti, Mother Pedroti, and he's like, must be a family textbook. And then there's another name Pedroti, and our classmate's like, little son Pedroti. It's just like, that's a great observation.
That's crazy.
Yeah. He definitely thinks.
He loves joking around. Yeah. He thinks outside the box for sure.
Yeah, most definitely.
Yeah.
Most definitely.
He described the furnace as a pressure cooker. I was like, okay. He's like, we're cooking up materials, we're cooking metals or magnets. And I was like, when I talked to someone, I told them we're cooking magnets, and I was quoting Dr. Tej.
Yeah.
So it was like, it was confusing, but I like the description. And also, he described the skyrmion when he talked to us about that at a conference as a spiny hedgehog.
Yes.
Texture.
Yeah.
Because it's spiky and the spins are pointing in all different directions.
Mm-hmm. Yeah, he's really great to go to conferences with. He'll tell you, like, you should go, you should be in this talk, you should be in that talk, you should, and then, when we were at lunch or dinner, we just bombarded him with questions, and he would just answer them and just have, like, almost answers to everything, which is crazy, especially whenever it came to magnets, right? So, yeah. So Anjali, have you decided what you want to do after your bachelor's?
I just asked you the other day.
Yeah.
You did?
Honestly, I feel like I don't ask other people this question as much as I feel I get asked.
Well, I know me and Tej ask you a lot.
Yeah. I want to find a company, which I have not done yet.
Okay.
Well, first I want to do an internship with the company.
Okay.
Then I want the company to pay for me to to work on my PhD.
Oh, PhD. Yes.
Okay.
I want to skip the masters and go to the PhD too.
Okay. Heck yeah.
That's my goal, and I feel like they need engineers, so I'll be able to do that. And they send those internship opportunities like in different states. Ideally, I want to do an internship in another state.
Okay. Hell yeah.
So, and I'll also material science.
Your family's okay with that?
Oh yeah.
Okay. Okay.
They better be. I'm gone.
Yeah. Okay. Nice.
I'm getting my experience.
I dig it.
And yeah, I really think material science is cool because to advance society and to like go to another age of technology, you have to have new materials to like see that vision. Like in the future, I hope it's not still brick buildings that we're building with, you know?
Yeah.
It's gonna look the same basic brick. I mean, that's gonna be great for aesthetics wise, but the future's gotta look different.
It'll
and
be
I
painted
think
with bricks. It'll be painted.
the paint is brick texture.
Yeah.
Wallpaper.
Yeah. I feel like when they do that now, it feels cheap.
Yeah.
But in the future, maybe it'll feel.
Yeah.
I think I don't know. But, I think.
Yeah, I mean, if you think about it, isn't it crazy? Like, for most of the history, we name a era based on materials: Stone Age, Bronze Age, Iron Age, yeah,
Yeah.
and out of nowhere we're like Digital Age.
Digital.
Yeah, we're building
AI age.
We should have just called it Silicon Age, no?
Yeah.
I would think it would be cooler,
Yeah.
right?
Yeah, that would make more sense.
It's a little more syllables, but yeah.
But is there but
Steel, bronze.
are we just
copper,
neglecting that there could be different ways to represent an age
time.
or a generation? Right?
Technology.
Yeah, I think that would be.
Yeah.
Well,
The Earth Age.
Because that sort of speaks to the type of materials we can manipulate, right? Whereas, yeah, there's the data age, and then before was the internet, the age of the internet, maybe, and then before that, the radio.
Stone Age, Bronze Age, Iron Age, Classical Antiquity, Middle Age, Early Modern Period, Modern Period.
This word modern.
But I guess Classical, Middle, and Early Modern and Modern, I guess they don't really have a specific material associated with it.
I feel like early modern would be like industrial.
Yes. Industrial is modern. Early modern is Renaissance age, so the age of enlightenment, the age of exploration. You know, when the science started booming, you get like people like Newton, Descartes, and all that jazz.
Maxwell.
Yeah. So.
Interesting.
Yeah, I feel like we should name it all in materials, right?
Yeah.
I think that would be cool. We need to find out what's the dominant material at that era.
Yeah, what is going to be the next material then, right?
Yeah.
So I like the idea of fungi.
Oh, yes.
I think they talked about it a lot in previous years, but like
fungal materials?
Yeah. Mushrooms to grow and like manipulating their properties to be more flame retardant, to take less water, to like be harder or softer.
Yeah, don't they have like mushroom bricks?
Yeah, they have mushroom bricks.
They have mushroom bricks, mushroom leather,
mushroom hats, and furniture.
Yeah.
I wonder if there's like a mushroom house.
There definitely is.
In my opinion, one of the most mysterious kingdoms in the Tree of Life is
fungus. My god, it's some video game.
It's ancient.
No. Mushroom brick material. Yeah. There you go.
I think you're onto something with this, Anjali. There's so much research going on in mushrooms right now, which I'm so upset at myself. So when we were,
there's a new mycologist on campus.
Really?
They just hired a new mycologist.
Wow. Okay. Cool. So when we were interviewing Dr. Waters, right? She brings up her undergrad's research that was looking at lion's mane as some kind of like, I think it was like a bacteria. It was like fighting against some kind of bacteria or something like that. Oh, it was to help fight cancer, I think.
I remember seeing that poster at like a research day.
Yeah.
And also, I listened to the podcast.
Oh, okay.
But, like, some of the teachers
but
skip me.
But I I neglected to ask her more about that research because I'm like really interested.
Time to invite her back.
In lion's mane, and I was looking it up the other day because, or like a week before we had that interview, I went down this rabbit hole of like, how do you grow lion's mane, and how would you? Because I take.
How would you cultivate it, right?
Yeah, because I take the lion's mane. They have a little vial, right, and you take in the alcohol and. Apparently, if you just eat the fruiting body, there's no like I think they call them adaptogens or something like that. The thing that actually gives you prevents neurodegenerative diseases and is good for your brain and memory. Like lion's mane really helps. Like I take it 5 days a week, and I think it really helps with my memory, my cognition. But if you take the fruiting bodies, it doesn't do that. But if you sort of do a alcohol extraction,
a tincture.
Yes, yeah. Then you can get those properties out of there. And so I'm like, okay, so I'm going to grow these things and have to do this alcohol extraction, right? And so I was going down this rabbit hole, and whenever she brought up that research, I was like, oh, yeah. And then like went into this rant about how you distill it and everything like that, and then we moved on to the next subject. And I totally forgot to actually ask her about the research because I'm sure it's interesting.
I find it fascinating.
Yeah, like how mushrooms can help with cancer. Like, wait, what? Because I think it showed that they did kill some cancer cells, which is insane. But yeah. Yeah, mushrooms are wild.
They have a lot of potential because there's so many different types, and I mean in Oklahoma, apparently there's like hornal. I forgot the mushrooms here. Morel.
Oh, morel mushrooms, yeah.
Yeah, and I was like, man, I wish I could see those. But yeah, there's so many different kinds, and they have all weird properties. Like ones that glow, ones that like they can survive on radioactivity. Like they take that in.
Yeah.
I guess the ones in Chernobyl. And like,
Yeah.
I'm pretty sure
It's
they're...
not. It is. Yeah. They have radioactive eating funguses.
Well, there's even ones that eat plastic.
Yeah.
Yeah, that they've been using to eat up the plastic in the oceans.
Yeah. And they also like grow really easily with sawdust and like dark environment or some moisture. And I see people like on YouTube growing them in buckets and in plastic bags. But for the radioactive mushrooms, like in the International Space Station, they run like water to block radioactivity in space. But they could also use mushrooms potentially and conserve more water in that way if the mushrooms are like surviving on radioactivity. And I think there is something like
surviving on radioactivity. Yeah. That's wild.
They could use mushrooms perhaps like to build modules on the moon if they can like use radioactivity. So
wow.
I think there is a lot of research there, and I want to read more into it.
That's insane.
Yeah.
So yeah, I mean that's pretty wild that it seems that there's almost a mushroom for every
problem
type of harsh environment and problem.
Yep.
Yeah. Like have you guys heard that we're some crazy percentage of mushroom or that like the tree of humans, like the tree of life, right?
So
it splits off from and then humans and then mushrooms. Like we split from mushrooms or something like that, right?
So basically that is still more up on debate for evolutionary biologists. Basically they're trying to debate whether the branch for fungal kingdom and the animal kingdom as a whole, how close are we? And at some point there was a research that showed that they're closer to us than we think, closer to us than closer to the whole animal kingdom, not humans. Animal kingdom.
I see.
Than we see. Because initially we thought they were far off. They're more closer to plants than us. But
the opposite is true.
Yeah. So some papers show that opposite is true. But it's still up for debate. It's a very controversial topic right now among evolutionary biology.
But I mean, think about it. Like our what do they call it? What's the system that goes throughout our bodies? The
circulation.
No, what are the little tendrils that go all throughout our body?
Veins.
What were you talking about?
The nervous system.
The neurons.
Right. The nervous system looks like mycelium.
Well, to be fair, I hear that argument a lot. It's like I think that's just the universe in general trying to find a way to minimize
energy. Yeah.
Yeah. So if you look at how the galactic filaments form, they look like neurons, right? But they also look like mycelium.
Yeah.
Mycelium looks like the tree roots and plants.
Yeah.
You know what I mean? So I feel like it's more like it's the same algorithm for maximizing surface area, minimizing volume. I think that's the main thing.
Same kind of math.
Same kind of math that applies for all these different systems. The most efficient way to organize.
Yeah.
So before we get into that, from what I found,
would you live in a house like this?
That looks fucking disgusting, but no.
Yeah. They just need to put some paint on the outside. Yeah. They could do a lot to change the
I
texture.
think they need to make it look less like a rotting corpse first. Then maybe I'll try.
Yeah.
But okay,
probably smells like one too.
So ChatGPT recommended some stuff. So he says that Stone Age will stay Stone Age obviously because it's based on lithic materials like rocks and all that. Bronze Age will stay bronze because copper alloys. And then Iron Age is mostly ferrous material. Makes sense. Now, Classical Age. What do you think? Classical Antiquity. What was the first thing that you think about?
Classical.
Is that like navigation, like the 1400s?
So it's like the early Roman Empire and all
very
that.
Classical, actually.
So what
is that? What is
material
that? 500 to 1,000? What is that?
What do you think should be the materials?
Bronze.
No, bronze is already over.
Oh, bronze is
bronze way earlier than that, dude. So stone, bronze, iron, then classical antiquity.
Oh, I guess it would be iron then.
No, iron's already over. Yeah,
really?
They already had iron.
Oh my gosh, I'm bad at this game.
That's the crazy part. Metallurgy is an old technology. People think that metals are some fancy. No, metals have been here for thousands of years.
Yeah.
So,
well, they weren't additive manufacturing back then. Yes. I know that's for sure.
The dominant materials of innovation back then is actually early glass and ceramic materials, pottery and all that stuff.
That makes sense, because they
bricks.
I think that's the first cathedrals with the.
Yes, and if you look at the Greek structures that stayed till today, and the Colosseum and all that, that's advanced ceramic. Masonry.
CM.
Yeah, and so I guess so at least ChatGPT suggests the ceramic age. Ceramics age or masonry age, and then another one is the industrial metal age. So they call it the age of alloys, but again, isn't copper like bronze an alloy age?
I would
steel age. It says. Anyways,
well, copper.
Carbon into iron makes steel, right?
Yeah.
Chromium, also like stainless steel.
Yeah.
For all the cutlery that used to be wooden or ceramic before.
So they call it. The suggestion is steel age, alloy age, or advanced iron age.
Interesting.
And then after that is polymer age or plastic age. Plastic age sounds cheap looking.
Yeah. I wish we could take that back. Yeah. We could just throw away that generation.
Yeah, and then finally is not finally, but after that is semiconductors age or silicon age, and then after that is biological.
But to be fair, the plastic age is due to oil, right?
Petroleum,
which is used in a lot of medicines and things now too, and so I would assume
age of synthetics.
Sounds like the age of robots or something like that.
Oh, true.
Oh my god. So speaking of robots and the topic of today, biomimicry, right? I have to look this up. So there's a really cool. So this, I don't know if it's cool, but it's definitely weird. So this hand that they built, I have to pull it up.
Is it from weaving?
The prosthetic hand. I'm gonna pull it up. 1 second here.
Is it from weaving?
I don't know what exactly they do. I think they just build like a skin. Or like, let's see here. So the title of the paper is a natural biomimetic prosthetic hand with neuromorphic tactile sensing for precise and compliant grasping. Yeah.
Ooh.
So here's just like a.
It doesn't look impressive. It just looks like a.
It looks like a
flat.
normal flat.
But I wonder. Oh,
Flexible.
I don't know if it's this or the video that I watched. So I'm either we're gonna look through this, and then if I don't see the image that I saw earlier, I'm gonna pull up YouTube.
So no, okay.
But yeah, look, it uses octopus skin or like I believe it's using ideas from octopus skin to
make the joints.
the joints. Mm-hmm.
Okay, the tactile sensor. That one's pretty interesting because there's already a material, pretty easy access for commercial applications. That when you stretch or bend it, it changes its conductivity. So I think what they did is they make it into pixels, pixels of it. So you can stretch any part that's individually. You get what I'm saying?
Yeah.
So it gives it ability to feel specific areas. See. Yeah, piezo-resistive. Yes, piezo-resistive material.
Yeah, so
cool.
It's like it looks like something you get from like a Halloween store or something, right? the fake finger.
No, I think the most.
This one kind of weirded me out too because I'm like, it looks like they grew this thing, but
no, it didn't. no. But I think the coolest part is the neuromorphic part.
Oh, okay, sorry. I think I went past that.
Yeah, that's cool.
Neuromorphic encoding.
Yeah.
So the analog sensing response from each layer of multi-layer tactile sensor was neuromorphically encoded relative to the
mechanoreceptors
in humans. Thank you. In human skin using the neuron model framework.
Neuromorphic.
How do you say that? Is Zikovich?
Where?
This one right here. Zikovich neuron model framework.
Zikovich, yeah. I would read it as Zikovich.
Have independently worked well with the texture discrimination, but we are using multiple neuron models to mimic the 4 primary
mechanoreceptors.
Thank you. Shown in further detail in materials and methods. So
interesting.
So this is to help sense. Is that what you're saying?
Yeah. So if you scroll down a little bit more, it can distinguish. So you see the bumps? It can distinguish the material texture. So this is a hard circular rounded ridge. Yeah. That is a hard 3 sharp triangular ridge. The AI or whatever model, or maybe it's just a signal. Maybe it's just purely the signal that's able to show. That's cool.
Yeah, really cool. Okay, I gotta find. I think it was a video then that I saw. Oh yeah. No. Here, he's actually like this thing looks.
Gnarly.
It looks like hot dogs, like little.
It's like shrimps to me.
Yeah, it does kind of look like shrimp too. But
it look like imitation crab.
Yeah, I agree with that.
Okay, let me pull up this video that I watched earlier. Let's see here.
That's cool.
Yeah.
History. Okay, that was the muscle that it was.
The biological age is making.
Okay, well
makes a lot of sense.
Here was another cool one though.
They made biological muscles.
Oh.
Battery high.
Super strong.
Oh, are we on here? Oh, my sound's off over here.
Bodybuilders jealous. These artificial muscles are able to lift 1,000 times their own weight. They are stronger and can expand 15 times more than natural muscles.
And they look so simple, right?
The strength and agility of these muscles do not diminish even after thousands of use cycles, which just goes to show how durable the material is. It is expected that these muscles can be bundled together to create more powerful solutions capable of lifting heavier loads. The artificial muscle was built around a core of fiber.
Yeah, that's weird, huh?
These fibers are made up of cheap and lightweight materials such as bamboo or silk that can stretch like a muscle. The core is then covered with a thin sheath of material that is the active part of the muscle. This sheath can respond to heat or electrochemical changes. When researchers applied or removed heat, the muscles contracted or relaxed.
Heat
much
is
like
interesting.
biological ones.
Yeah.
Like,
Have you guys
how sensitive?
have you guys watched a Project Hail Mary yet?
No, I haven't.
No,
I heard it's great.
Every time,
dude, it's in theaters.
Yeah, you
Come
guys
on.
have to watch it. It's good. No, you have to watch it in theaters. You have to watch it.
Okay.
If you can watch it in IMAX, watch it in IMAX. I don't know if it does, but it's so good. But anyways,
Facial muscles. Yeah, because this reminds me of this thing right here. Have
yeah,
y'all
that's the
seen
one I
this?
was talking about, the weaving one. Oh my god, that looks freaky.
Is this real? Like, is this actually moving like by itself, or maybe connected to something? But
So if you look, search up weaving robots, right?
well, because remember, Anjali, have you seen? You probably haven't.
Yeah.
Anjali doesn't watch any new things, so if she watches, Hail Mary, it's
It's on YouTube.
It's on YouTube.
let's see here, weaving
Robots.
robot. I was gonna say, have you seen
This
Westworld?
one. Oh,
West. Say it again.
Westworld?
yeah, you're
No.
talking about.
Oh, okay.
Yeah.
Yeah. So it reminds me of this. Oh yeah, Westworld is real.
This
Yeah.
startup just works out how to weave robotic parts rather than bolting them together. And it means that they can cut production times from weeks to just minutes. Most advanced robotics...
We're going back to weaving, man.
It's a bottleneck that makes robots slow to build, expensive to customize, and...
So they're able to make a robot arm in
Area
minutes,
US robotics
not
startup company
weeks.
called Solana
Wow.
is threading a different part. Their 3D tissue braiding method lets them make lightweight structural
That's
force
insane. So, like,
effectively
inside
with
it's
a
just,
robot
like,
braid, and
weaved
automate a braiding
fibers?
method
Yeah.
to weave multiple
See?
materials with different properties
Wow.
together.
And all the fibers are able to move because something's controlling it. Which is that brain.
This came from.
The team uses high
It's not moving very well.
Is that like if you? I mean, I guess that's how the body it moves the bones and the skin's just attached to the bone.
Yeah.
Structure during fabrication. These tendons can be contracted by motors located deeper in the structure. By adjusting the braid angle and using elastic fibers, they can control the degrees of freedom and angle that the joint can move through, recreating how human tissue supports and limits motion in our own joints. They can also include things like pressure sensors or conductive elements to allow sensing and signal transmission through the part of the body itself. As a result, they produce a single integrated structure, strong where it needs to be and flexible where it should be, with no assembly or tiny screws required. This is important because if robots are going to leave the factory floor anytime soon and work along us, we need bodies that are cheap, adaptable, and easy
from the
to make,
movie.
not hand-built relics of an industrial era. If you
Let's see here. So robotics is getting wicked now. Robotics, robotic arm, mixes, chemicals. Doing what you did just yesterday.
They're stealing your job, Anjali. What are you gonna do about
Oh,
my goodness.
what? I could, or maybe.
it? Oh, this is cooking.
Oh, it says cooking.
Yeah, this is cooking.
Oh, that's a video. That's a AI video. It looks like.
Well, they already do have robots that can.
Oh, here we go.
Oh shit, micropipetting.
Yeah. But see, the one that I saw, it looked better than this.
They're gonna do it way faster and way more precise.
Well, this doesn't seem faster because my lab mate, he
Yeah,
like what-
in the future.
in the future, yeah.
Let's
Well,
see
they
here.
do have large scale micropipetting for robots already.
Mm.
Like
They have a ton of them.
they micropipette like in rows at a time. You've seen that
Yeah,
before?
I've seen
Yeah.
that.
Okay.
Yeah, they already have that. It's just I guess it's more general.
I think this is the one.
has been tested over and over and over again to put this banana into the bowl. This is a very simple task.
Today, we've reached a new milestone.
Wow.
We're introducing Gemini.
This isn't the video, but
The robots that do surgery on like corn, and it's just
Oh, yeah,
they're
I've seen
able to
that.
beat that.
on and like on a single piece of corn, right? Like, and it was.
And it stitches it up.
Yeah.
The surgery.
Yeah.
Yeah.
Insane.
There's also another interesting thing is there's also another interesting thing is, 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 there Okay, wait. You search up your thing first. I'm gonna look for it. I'm gonna look for it.
Well, so I just wanted to ask Anjali. So, Anjali, you're the one who proposed this idea. Why?
I think like philosophy-wise, nature has so much to offer because, I mean, a lot of articles they say like billions of years, the math of the universe, it's been perfecting itself, and through evolution, like the systems that nature builds are really good, and they just keep improving like that. So why shouldn't we look to nature for like those principles that work and are proven to work? And like we use nature as inspiration for everything we built.
Okay, so have you seen a flagellum?
Like the tail that moves the
But on the molecular scale.
on the
Or
molecular scale.
ATP synthase. Have you seen that?
No, I don't think so. Not
So-
that close.
What do I need to look up?
Flagellum.
Flagella.
It propels the
Flagellum structure.
cell.
Oh no, go to images. There should be GIFs, whatever you. Whichever.
You mean photos?
Can you go to search GIFs?
Okay.
There you go.
Is there a robot like
yeah.
this?
Oh, that one's a good one too. Let's see here. See if
So-
we can just visit this.
They are microscopic motors.
I want this. Go away.
ATP synthase is also a microscopic motor. Do you also mind pulling up ATP synthase?
Why don't it just let me see?
Yeah, just search up ATP synthase. That should be it. ATP synthase is usually better. ATP synthase structure. Oh, that's GIF.
Is it GIF or
ATP?
GIF?
GIF.
Anjali? Yeah, GIF.
My bad.
GIF team, let's go.
My bad. Okay, so anyways.
GIF is peanut butter.
Yeah, there we go.
Oh, really?
Which one?
Just go images, I guess.
ATP is like the energy.
Yes. This thing creates ATP, and look how it does it. Do you maybe
this one's pretty.
Do you see it rotating?
It's that
Let's see. Open.
brown thing is rotating
Yes.
the whole top bit.
It uses hydrogen nucleus, so protons, hydrogen ions, flows through it, right? The hydrogen ion flows through it and it rotates. And inside its structure, it has something called a proton wire. The proton wire conducts positive charge. It conducts protons instead of electrons.
Wow.
Nature already has wires, and at least something that's similar or analogous to wires, and it is literally a motor.
Dang.
It uses the high electrochemical gradient of the proton concentrations outside of the matrix membrane, the mitochondrial membrane, and molecular motors. Yeah, see.
Wow.
So that's the flagellum. That is the flagellum.
Whoa.
So this is just a motor protein. So when you do biological motors, it just shows motor proteins. So that's a. But yeah, this is a flagellum, and it's able to reverse.
Wow, it can control.
It can reverse, yes. So that thing that spins, to reverse, all it does is it moves inwards, and when it moves inwards, it starts rotating backwards.
That's insane.
Right, and that's why it just makes sense to me that building engines and mechanical structures like this that we humans do, right? It just feels natural, right? And I wonder if it feels natural because it's something that's sort
Already
of
been
a part of us.
Yeah, we have that ATP synthase in almost every living organism on Earth. ATP synthase is there, and flagellum is also in almost every living organism.
Wow. When did they discover that these things look like little motors?
That's a good question. It's like mid-90s, not mid-90s, mid-1900s, like discovery of flagella. Structure. So they know they whipping around. They just don't know how it works, and they discover it around 1970s.
Wow.
And in fact, back then, this was so mind blowing.
How did they see that?
Electron microscopy.
Wow. Okay. Yeah.
Okay. Actually, go to Google. There's actually, yeah. See, it says so go search electron microscope.
Yeah.
Flagellum.
Okay. Oh my gosh, can't type today.
Electron transport chain is also very interesting, but we'll talk about that next time.
Scope. What did you say, flagellum?
Flagellum.
The proton charge is being
This right here?
conducted.
The
Flagellum.
second one.
This one?
Yeah. They even have videos of it.
Oh, I want to see that.
Well, not really videos of it. It's more like videos of bacteria.
Hype train over here.
So no, so when you go search a electron swimming, so not electron swimming, bacteria swimming. Swimming under microscope. No, these are not bacteria. These guys are lying. Scroll down. I need to find it for you. It's okay. So first, I want you to look at the. It's not those. Okay, I'll search it while you look for it. But you look at the electron microscope one, the other one that you pulled up. You closed it. Yeah. So isn't that crazy how you're able to see in such detail using electron? So video.
Pretty wild. Oh, here we go. Flagellum basal body.
So is the only energy like the cell is exerting is to like bring itself, like to reverse it, it brings itself inward?
What I mean by so they have little motor-like proteins that spin in the presence of either ions or ATP, and what happens is this is the flagellum itself. It rotates like this, right? It rotates like this. This is the motor. It moves inwards like this, so it moves with it. Does it make sense? That's a better animation. Go YouTube this time. Just search flagellum.
Flagellum.
Structure. Oh wow, that's fine. This one, yeah. This one, the second one. Well, this is a weird edit. Yes.
Yeah.
Someone made a weird edit, but I don't want to get us copyright striked.
Yeah.
So
apparently, if you hum a song now, you'll get you'll get a strike.
Oh no.
Yeah, it's kind of crazy.
It's a bad humming.
Just by humming a song.
starts humming.
They're listening too hard.
But interesting. So Anjali, is there a specific like multiple specific ideas in this field that you're interested in, or just find fascinating?
I don't really have any to tell you. I think just like, okay, I guess it's the cartoon show Wildcrats.
Okay.
You know how they talk about every animal has their superpower?
Yep.
I feel like that's a great idea. That's really cool. Why don't we try to like replicate those? So like small birds that can fly a long distance, how they're able to like.
Is this it?
Yeah. No, Wildcrats. Krats.
Okay.
Yeah.
Wildcrats.
It's on PBS.
Oh, okay.
Yeah. So literally they engineer discs and it has those animal superpowers. They transform into the animal, and like if they're a cheetah, they have the speed of a cheetah.
Okay.
They literally become a mech version of the animal.
Okay, so it's kind of like what was the show? I wanted to say Power Rangers for a second, but yeah.
My friend Michael, he really likes the Power Rangers thing.
So we're in our microprocessors project. We're making our microprocessor essentially play a bunch of different theme songs.
Oh.
And so the Power Rangers theme song is one of the ones we're trying to get it to play.
That's great.
Yeah. But okay, yeah. I mean that would be pretty wild, right? To have like almost like superpowers, right? But how would you even go about that?
A lot of engineering.
Yeah. I mean, that'd be like some gene engineering. It's
Yeah, definitely not like how they do it in the show.
yeah. Yeah, I feel like the first version of that are like attachments. Or like you go get your nails done and you have like
Yeah. Like it would have to go gene and editing like you said.
Yeah, so let's see here. So I found a couple of things that I thought were interesting. Let's see here. So for one, there was like an example. So where this field is going to is like materials and like materials that can heal themselves. Which I thought was pretty cool.
Bacteria materials.
I don't know specifically, but maybe. Let's see here. So materials that heal themselves.
There's a concrete I read where there's bacteria in the concrete.
Oh yeah, self-healing concrete.
Yeah.
That's so cool.
Really?
If there's a crack, then it absorbs
Water and then
Self-healing
the
concrete.
Yeah.
Oh.
The concrete awaken when they come into contact with water. These bacteria then produce calcium carbonate. The calcium carbonate fills the crack, allowing the concrete to effectively heal itself. This extends the lifespan of structures, reduces maintenance costs, and minimizes environmental impact.
We need it on campus.
Yeah.
When cracks form,
Real.
bacteria
The
within
potholes.
concrete
If
awaken
potholes fill
when
with
they come
water,
into
like-
contact with water. These bacteria then produce calcium carbonate. The calcium carbonate
that's
fills the crack,
reading.
allowing
That is insane.
The thing.
Okay,
I
this
guess.
one's cool though. Self-healing fabric.
This one?
Not seen this.
So, okay, I don't think this is real.
He's
but that's
rubbing the bottom of
so
it.
that's another one that is that's a different one that is healing because of heat.
So self-healing fabric?
Yeah. Polymer.
Oh, okay.
Does it shrink over time?
That's a good question. Yeah, so it
This
uses
is a strip of self-healing polymer. That means I can slice it into two pieces, and then with the application of gentle pressure, push the two pieces together, and it will become once again one
Heat.
single piece.
So there's another one that's
You
heat.
might think,
This one is
well,
just
that's not
pressure.
so
Oh, just
That's
pressure.
not even that
If I
much
took a
heat.
strip of blue tack,
Well, there's definitely pressure that,
and then press those two pieces
or
together,
heat that
I would once again have a single piece of blue
would I
tack.
would think help,
I
right?
might
Heat
also
from the
say, look,
pressure
I
that.
have two droplets of water and I push them together, they become a single droplet of water. The difference between blue tack and this self-healing polymer is that, well, blue tack is sticky. It sticks to my hand, it sticks to a wall, it sticks to the back of this picture of Patrick Stewart. So it's not surprising that
It does.
sticks to itself.
Picard.
This polymer isn't sticky. The same goes for droplets of water. They're sticky and they flow because they're a liquid. So we should naturally expect different behavior from droplets of water as we do from a strip of polymer. We can actually flip this question on its head. Instead of saying, why is this polymer self-healing? We can say, why aren't other things self-healing? Why isn't metal self-healing? Like, if I cut this piece of metal in two, why is it that I can't just...
Metals are actually self-healing if it's in vacuum.
...fuses back into a single
Whoa.
piece of
What?
metal?
It's called cold welding.
What's happening at the
yeah.
level, a metal is a lattice of ions in a cloud of mobile electrons. So if you slice this lattice in two and bring those two ends back together, well, to me, that looks like a single metal lattice. So why doesn't it become one? In the case of metal, the answer is actually quite straightforward. It's oxidation.
See? The oxidation layer is what prevents
It's
it.
soft enough to cut with a knife. And when I do, you can see it's actually a really shiny metal, but that doesn't last forever. It doesn't take long for that shiny
What was
surface
that?
to become dull.
What kind of metal is that?
That's like sodium
because the metal
or potassium.
is reacting with oxygen in the air.
It looks like
Actually,
cake.
the same thing happens when you
Yes, very
any
soft.
metal. It's just that oxidation layer isn't as visible in the case of, say,
Whoa,
steel.
you can see it oxidizing. I don't know if I've ever seen.
Then that if you took two pieces
Yeah.
of metal, and
So
Okay.
in space, if you take two pure metals, put
Yeah.
it together, it'll weld back together.
Wow.
So
So why don't we just create space here on Earth and
we'll
then...
die. So can you search up one last thing?
I'm saying like in a small area. I'm not saying
a
the
vacuum?
whole...
No, people have done it on Earth.
Really?
They weld two pieces of metal together just because it's like pure cold vacuum.
Can we look that up really quick? I wanna,
Cold welding?
Do they do cold welding like?
It's not practical. It's not that practical. So in space.
Building in space.
Yeah. So that's the one.
This one.
On the right. Yeah.
This one. Whoa.
See, the metal lattice just becomes one.
Wow.
Man.
It sort of looks like fluids coalescing.
Yeah.
But this is because so this is replicated on Earth. And it makes sense because it's Earth. It's hard to replicate pure perfect vacuum like space.
Yeah.
Well, even space is not perfect vacuum, but you get what I mean.
Yeah.
But yeah, it's what he showed was correct. So if you take two pure metal lattices, put it together, it'll just stick.
That's insane.
So can you switch bacterial
But that was like a
hydrodynamics?
very... I mean, that was microscopic, right? So...
Yes, at large you can do it.
You can enlarge?
At large,
Really?
yes,
Okay.
you can do it. It's just no one has done. I don't think anyone has done it. Maybe you have to search up large
Large.
in space or
And
cold
in
welding in
charge.
space.
What if they had like a factory in space where they cold weld materials and then they just send it?
Or whatever.
That would be cool, but that means anyone there has to be operating in vacuum. So if that were to happen, either we have to be in a spacewalk the whole time, which is kind of dangerous, or we have robots do it.
I think we got our solution. I feel like biomimicry will like robots and materials. About so far.
If two metal...
But I don't think. Yeah, none of these are real.
Yeah.
All these are,
That'd be fine.
yeah, but the microscopic one's the real one.
Well,
So-
space.
Yeah. Anyways, the final thing I want you to search is bacterial. Oh, that's not the final thing actually, but it's okay. Bacterial
I'm about to say we done it already.
hydrodynamics.
Bacterial what?
Hydrodynamics.
Hydrodynamics.
Scroll down. It should be the first one. Yep, this one.
Whoa.
You can see that little guy swimming.
Whoa.
It's slowed down though. This is slowed down.
It's so long. I thought it'd be shorter somehow.
Oh yeah. Most of the time, the filaments is longer. The flagellum's longer than the bacteria.
And this is from 1970? It looks like it would be.
So this is from a. So if you look at that's a 9-second one.
10 years ago, it says.
There's yeah, it's from one of the papers. So that second one, yeah, the first one.
Oh, you said the second one, not?
So second one because it's supplemental video too.
I see,
Yeah, this is the real speed I think.
Okay. Wow, they go pretty fast.
Seeing that in a microscope would be crazy.
Can you swim that fast?
And here's the crazy part,
Yeah.
because they're so small, water tension
Yeah.
is like swimming in honey or peanut butter. In the perspective of bacteria, they're not swimming, they're digging.
Ooh.
Because
Okay.
because they will be swimming in molasses.
Yeah.
It's at that scale.
Interesting. So,
Yeah.
Anjali, do you know when this idea of biomimetics was coined?
No.
Trivia time.
I don't. In fact, I didn't really know it's called biomimicry, so I'm pretty sure Albert, you know more about this.
No, I actually don't know when.
And whenever I was looking this up,
1970s.
you said when?
I'm gonna say 1960s.
Okay, pretty close. 1950s apparently.
Oh, wow.
So now, can you name the guy who coined it?
No.
Definitely not.
Is it a Japanese guy or something?
No, Otto Schmidt. Let's look him up.
Otto Schmidt.
Otto
I'm racist. I was like, Otto? Must be Japanese.
Otto Schmidt.
Oh, this guy.
That's not how I thought Otto was spelled.
Oh, there's not a picture of him. But anyways, was an American inventor,
Biophysicist.
engineer, and biophysicist known for his
He's a
scientific breakthrough in biophysics.
He established biomedical engineering.
Okay, see, you should know about this guy.
Well, my bad.
And coined the term biomimetics, which was later called
Cool term.
bionics by Jack E. Steele.
I still prefer biomimetics, low key.
Yeah.
Jack E. Steele, the first one.
Bionics.
Yep.
Yeah, bionics, yeah. They didn't even have a picture of him. That's messed up.
That's messed up.
Yeah.
Who the hell is he?
Steele as his last name.
True. That's pretty. Yeah. That goes hard.
Attended Mendota.
Work on bionics and research on cyborgs.
Until he joined.
That's fucking dope, dude. Imagine having in your bio, I work for. Imagine he says that I work for the Air Force. I was a colonel. I work in neurology, and I work. Wait, what did he say? Cyborgs. He does his research in cyborgs.
Oh,
I'm surprised
yeah,
cyborgs
right
was a term. Oh wait, it's a 1972 book.
Yeah.
Like, that's not 1950s.
1972 book, Cyborgs. What? Science fiction?
Star Wars.
Makes explicit reference to then Major Jack Steele. Oh, I gotta look this.
Cyborg.
Let's save this.
Was coined in 1960.
I'm gonna save.
Because he did research with the Air Force about cyborgs, real cyborgs.
Interesting.
That's cool.
Yeah.
And he worked for the Aerospace Medical Research Lab.
That's fucking dope.
Yeah, this guy seemed.
It would be crazy to put down on your resume.
Not a big bio, but man, it sounds like
he did a lot in a short time.
He had a lot of interesting
life.
Yeah. Wow. Cool. So because whenever I was asking ChatGPT about this, I was like, hey, so what is the idea of being able to look to animals for engineering ideas? And it said biomimicry, which biomimetics, like what does biomimetics mean?
Mimicry, mimetic.
Mimetic is mimicking.
Yeah. So anything mimetic is anything that can mimic.
Okay. See, biomimetic sounds like the more scientific version of biomimicry.
Yeah.
Biomimicry is like the layman term. It feels like. But then let's see here. So. There was.
Yeah. No, it was correct. So mimetic comes from the word mimesis.
Mimesis.
Yeah. So it's if it's where a living creature mimics the form, color, or posture of their surroundings to avoid being noticed. So biomimicry is technology trying to mimic biology.
I see. And then I guess in 1997, Jane Binyas came out with a book called Biomimicry. Oh, wow. Let's look at this. And after she published this, this is when this biomimetics actually became popular and seen as a fruitful endeavor. Let's see here. It's American Natural Sciences writer. Okay. Intentional problem solving, design inspired by nature.
Godmother of biomimicry.
It's modern, but I feel like this is like civilizations have done this since humans have existed.
Yeah, that's what's interesting I
don't know what they would call it though.
Yeah, because it makes it sound like we didn't start doing this until 1970, or when did I say 1950s?
Yeah.
So, yeah. I mean, because think about it, right? There was Leonardo da Vinci, right? He had sketches of wings. And trying to use them to fly.
It's more, yes.
So that's
that is biomimicry, but I think they popularized the idea, the term. People have done it throughout long time. For example, when we try to paint ourselves to look like the environment to hide from animals when we're hunting, or when we use animal skin. Because we want to, like, let's say we wear like
biomimicry.
Yeah, that is biomimicry because a lot of animals they camouflage using the color and patterns of their fur. Because most animals are colorblind. Yeah. So because they can't see like us, but if they can see like us, they can easily spot.
Yeah. Huh. So another trivia question, Anjali.
Okay.
Would you consider Velcro biomimicry?
I I read about this, and yes.
Okay, yeah.
Because, like, the guy saw burrs stuck to his animal's fur.
Yeah.
And so he was like, it like, hooks onto things.
Mm-hmm.
He looked at it closer.
Yeah, whenever I read that earlier, I was like, wait, what? So Velcro came from...
And Velcro's so useful.
nature.
Like,
it really is.
That's like an amazing...
As long as you get good Velcro.
Yeah.
If you get bad Velcro, it's like, it's your worst nightmare.
It doesn't do anything. Bad Velcro.
Yeah, it's not doing very good biomimicry, that's for sure.
Good.
Let's see here. There was another really cool. Let's see here.
I feel like basic bugs, like waters, gator bugs, they stand on the water because of the surface tension.
Yeah.
They use simple physics. I mean, it's not simple, but for them.
Yeah, right. Because they're so light, right?
Gecko palms.
Yeah.
You know those like things that we used to climb on walls.
And you know what's wild is
Tiny.
apparently that's like one of the most researched fields or ideas in this biomimicry field is gecko stickiness, like hand stickiness, right? And I believe there's even like a really good actual product out there. Gecko gecko hands? I don't know.
Gecko tape. Medical bandages.
Living
Microscopic hair covers their feet.
artificial gecko skin. Oh yeah, Vertasium did a.
Hey, everybody's familiar with it. You press it on, and it sticks pretty hard actually, and then you peel it off. And here's gecko material. And the first thing you notice is that it's not sticky at all. But if I lift it from the middle, I can lift a football. You might say, well, you could do that if you had this other sticky tape, right? Well, yes, but if I had the other sticky tape, it wouldn't do that. And that's important because if you're a small robot trying to climb a wall, you can't afford to have something like chewing gum on your feet because then every step you take is effort. What you want is something that only grabs when you need it to. And that's kind of the main principle of our gecko-inspired adhesive. Here, this is an early prototype of the StickyBot gecko-inspired robot. This got us into a long effort to understand what is it that makes gecko adhesion work, having something which grips but is not sticky.
Geckos.
So
beautiful.
There's also this idea in this field, or this conversation, I guess, that goes around in this field, and as of late, or that's what I read anyways, is that we've, for a long time now, been only focusing on sort of animals we admire. And, so the field is starting to expand now and to look at a variety. Oh, my bad. He scared me. A variety of different animals and organisms to start trying to get principles from. And so yeah, that's interesting. And what I love really is I didn't really realize that it touched material science as much as it does. We looked up the concrete, and people are getting more involved in how can we sort of learn from the different materials to be able to do, I don't know, cool things. Let's see if I can find the one that I was looking at earlier. This is what I want to biomimetic materials. Have you ever heard of nacre-inspired toughness?
I'm not.
Nacre? Yeah, nacre-inspired.
I feel like I have seen that.
Nacre is the type of material you find in shells, yeah.
What?
Shells are tough, and they secrete it. And the way they secrete the layers.
I know ancient people use nacre for decorations, but I didn't know that modern day people are making
Interesting. Well, I don't feel like these are good. Well, let's see here. What does this look like? Electromagnetic 2D Knacker inspired films. This doesn't really say like. Are they coding this stuff? Are they coding the Knacker onto things? Is that what they're trying to say? Okay, I'm just gonna ask ChatGPT. Knacker-inspired toughness means making a material tough by copying how Knacker works. Knacker is mother of pearl, the shiny inner layer of some shells. It is made mostly of a brittle ceramic-like material, but it does not fail as easily as plain ceramic. This is the trick. Why it is tough. Knacker has a brick and mortar structure. The bricks are stiff mineral pallets. The mortar is... Oh, platelets. Yeah, thank you, Anjali. The mortar is softer organic layer between them. When a crack tries to move through it, the structure forces the crack to work harder instead of one clean. Straight. Okay. Interesting. Inspired toughness is enhanced crack resistance.
So if there's a crack, it'll secrete more Knacker in that area?
Yeah.
I guess so. Weird.
Here's some do you know mechatronics?
Yeah.
Right? A lot of biomimicry actually comes from mechatronics.
Okay.
So there's this guy, very small YouTuber.
Mm-hmm.
He rushed his final year project using biomimicry.
Okay.
So do you mind going to YouTube?
Yeah.
TAZER. Just one Z actually. My bad.
Yeah.
Underscore clips.
Jesus.
And then engineering. Space engineering, yeah. Now, go to his first one, yeah?
I love
So go to his shorts. Go to his shorts.
It kind of looks like Timu.
Yeah. Timo.
Timo. Yeah, that's what it is.
Go to shorts.
Glasses on him.
Oh, shorts.
Yep. Scroll down. Go to that gripper one.
I'm building a biped robot, so I don't get.
What the fuck? You're lagging. You gotta restart it.
The main thing I'm building a biped robot, so I don't get fecal with him.
Oh wait, it's not this one.
Still pretty cool though.
He made he made a bipedal robot. He made a hexapod crab thingy. He also made a gripper.
Yeah, I've made one of those.
So the one I wanted you to watch is the gripper, but I don't know why. Yeah, that.
Engineering school project on last day. This project is for my smart materials class, and it's a smart gripper. After doing some research, I decided to copy this Festo design. It is made out of a soft material, and because of its special structure, it can adapt to any object it grabs. After 3 years,
it's called counterbending.
Of videos from TPU, I was happy with the design and started modeling the rest of the gripper. As you do the servo motor, the gripper closes and goes to the front a bit, and since there are these 2 gears, it's gonna move the second side as well. I assembled the gripper, and after making sure it works, that's actually pretty good. It was time to add some sensors. I decided to use a thermistor for measuring the object's temperature, and I also added some EDS foam.
This was his mechatronics project?
His mechatronics smart materials project.
It's not literally on the last day, is it? Because it seems like a lot.
Oh wow, it's working so well. And since some of my teachers actually watch my videos, this is a joke, and I made the gripper work the next day. The orange line.
Did he say he made it in one day?
No, it's clickbait. He said it did it last day, but he did it in like last few days though. He did it last few days.
And the blue line represents the object's temperature. Final suck, I had almost no time to make this gripper, and this is why I tried speedrunning my engineering school project on last day. This project is
so that's also biomimicry. That's just another example.
Yeah,
so he used a thermistor. He used a thermistor, and then he used the piezo-resistive material that I told you guys about to make the gripper be able to feel an object's temperature, feel an object's texture. Well, not texture, the force it's applying.
Yeah.
So if you think about it, haptic feedback, like feeling a texture on a surface, is just multiple tiny piezoelectric sensors, piezo-resistive sensors. So you form pixels of those pressure sensors instead. So that's so he didn't do that, but the other video, the other paper that you showed, the finger that can feel, that's what they did. They used that same material that he used for this gripper. Instead of one big one, the research paper made multiple. So it acts more like a pixelated pressure sensor instead of one big one.
So you have more data points.
Exactly. Similar to how your trash can thingy, it cannot correct itself because it only has one sensor. If you have like 3 to 5, it can at least track, the gradient of change.
Like a satellite.
Yes, exactly. You need minimum, that's at least like, in 3D space, you probably need like 4 data points. In 2D space, I think you need 3. Yeah, because you need to triangulate a position. So yeah.
That makes sense. Interesting. Yeah, I mean this topic about biomimicry is kind of wild. So let's see here. There was some. This was interesting. So let's see here. The Kingfisher-inspired Shinkansen nose.
I have no idea what it is.
Yeah.
Never even heard of it.
Before I look it up, you guys guess what maybe this is?
What, say that again?
The Kingfisher-inspired Shinkansen nose.
No
Kingfisher is a bird.
I think you're onto something over here, Anjali.
Is it aerodynamics?
Oh, whoops. We're about to find out. Is it about like aerodynamics of a plane? About to find out. What do I keep? Oh my gosh, I'm sorry. I keep messing this up. Oh, I put it in the middle. Wow, that is so ridiculous. There we go.
Aerodynamics.
Yeah.
Well, it's not on planes.
So is there a high-speed train inspired by? Yeah.
Interesting.
Wow, their nose is quite long.
In 1989, Japan's Shinkansen bullet train had a problem. It was fast, really fast, like pushing 170 miles per hour fast. But every time it exited a tunnel, it was loud. The noise was coming from a variety of sources, but whenever a train sped into a tunnel, it pushed waves of atmospheric pressure through the other end. The air exited tunnels with a sonic boom that could be heard 400 meters away.
Wow.
In dense residential areas, that was a huge problem. So an engineering team was brought in to design a quieter, faster, and more efficient train. And they had one secret weapon. Eiji Nakatsu, the general manager of the technical development department, was a bird watcher.
Bird watcher. How long is
Brother brought his hobbies to real life. That's awesome.
Yeah.
That's what I want to do.
That well, Bill?
Yeah, so it was a bird
design.
Yeah, bird beak
design.
Inspired train.
Wow.
Nose, yeah. And so apparently this is like one of the more famous of the biomimicry applications.
Huh.
Yeah. Really cool though. And I don't know. It's just,
why isn't? I know planes are already pretty aerodynamic, but I don't see planes using that. Why?
Well, I mean,
right?
So let's see here. Do they have a?
Because they use it in.
But don't like fighter jets look
fighter
like
jets, but commercial planes though. I know some private jets look like that, but does all commercial jets look like that? Or maybe just a fatter scale.
To be quieter, so.
Quieter, so more efficient, right? No use.
No use, yeah.
Why do commercial planes no use?
Airplanes live in another.
It was mainly about when a high-speed train. Yeah, we know that part. Here's the heart of it: planes are not entering tunnels. Oh, well,
What?
yeah, that's maybe why.
Entering a large fluid.
So
this reason for that shape mostly vanishes. Okay, that makes sense.
Okay, it also makes sense why fighter jets need it, because they do go supersonic.
Yeah. Okay. Yeah, and so they are pushing that
They make their tunnel in the air.
Yeah, because of how fast they're going.
They're making the Mach cone.
Which is kind of wild that we don't have a high-speed train here in America.
Yeah.
That is pretty insane. Because when I first heard about the bullet train, I was like, it has a bullet in its name, must be America. And then I looked it up. I'm like, it's Japan, it's South Korea, it's Taiwan.
Have y'all seen
China.
videos of this thing? Zoom in.
Yeah. It's like,
I don't
gone.
think
Oh, okay.
It's like-
Anjali, I gotta show you.
it's when you think it's fast, it's not fast enough. It's really fast. Like,
what the heck?
Goodness.
fuck.
Do they feel like normal in there?
In there it feels normal because the acceleration isn't fast. It's just that because the thing you feel, the kickback is acceleration.
Yeah, this is the best one.
Yeah. So this is.
That's so crazy. And it's a long train.
To be fair, it may not sound that impressive, but this is the first time they had a bullet train. So it's probably a big deal back then. They're like, oh, they made the face like,
Yeah.
Look at the reactions.
It's so crazy.
They're like, what?
So
World's fastest train. All right. Really, really building up the suspense here.
It probably already passed by.
That didn't look too well. Probably
fair,
because
they're near a station.
They're following. Yeah, they're probably slowing down.
They slow down at a station.
Yeah.
So so this is
this motherfucker.
320.
That is a future trip.
yeah. That is what happens when it enters the tunnel.
Yeah.
That pressure wave.
Yeah.
That is so crazy.
I mean, how would you feel being on one of those? Would you think you'd be a little nervous?
Well, to be fair, when you're flying on a plane, do you feel nervous? Yes. Right?
No, not really, honestly.
Well, a lot of people do, but
Yeah.
I don't care because I fly on planes all the time. But I'm pretty sure like this is way
jet life over here.
No, I have to. I live across the world.
Yeah.
But this bullet train, I feel like it's probably safer because you're anchored by magnets.
You're on the earth.
This thing looks like a platypus.
Yeah. It
It's
does.
hovering.
Yeah, that makes sense.
Yeah.
It's hovering above it.
It's not. Yeah, it's hovering. It's
But tiny. Really.
Yeah, and it's not hovering the way people think. Because when you put two magnets together, they fly off, right? At least they repel. But these are not repelling. They're hovering, like what Anjali says. It's
So no
quantum
friction.
locking. They call it quantum locking. Have you seen those demonstrations where they put a superconductor on a magnet and it just stays there?
Yeah.
You can't push it, you can't pull it. That is quantum locking. It's I think it only happens in type 1 superconductors or something.
Yeah, that's right here.
In the last video, I showed that if I put a magnet...
Quantum locking right there.
it
Beautiful.
floats like magic. What I want to do now, though, is show what happens if I do it the other way around.
See, it just keeps rotating.
For this one, I'm using a much bigger superconductor, and I'm again cooling it with some liquid nitrogen.
Oh, that'd be cool. Anjali, get us some liquid nitrogen.
They have
We do it.
in the
We do
chem
have it
department.
in the biology department.
Oh, we gotta do this experiment.
It actually stays on the track,
The
and if I
huge
push
canister.
it, it's able to move without falling off. It's also surprisingly strong, and even if I push it decently hard, I can't get it to touch the track. As it warms up, though, it eventually loses its ability to superconduct, and it stops floating.
What if we
In the last
could
video, I showed
take that to a school and demo that? Have the cloud chamber, have that, and
Because both are cryogenic.
that would be so cool.
But
How many minds would that blow, right? Oh my goodness.
My biggest thing is why aren't you using your little simulation, right, to try to look for room temperature superconductors?
Oh,
right? You're looking for magnetic materials, but high temperature superconductors. No one's doing. Well, not I wouldn't
High
say no one.
temperature.
So by we already have high temperature superconductors, but by high temperature, they are talking about warmer than liquid helium.
Yeah.
Oh.
So that's what it
Closer to
means.
room temperature.
So we don't have that.
Yeah.
No one has. Not even close. The room temperature superconductors we have has to be under 2 gigapascals of pressure. So that's like 20,000 times.
No.
I guess so. So you think that I could use Ising model simulations for that?
Do you know why? Because magnetic fields usually strong magnetic fields usually destroy type 1 and type 2 superconductors. But here's the thing. High temperature superconductors, they are what we call non-trivial superconductors because they are not formed by Cooper pairs. Because normal superconductivity comes from Cooper pairs. Non-trivial superconductors, we have no idea how they work. We honestly have no idea how they work. No one has an explanation for it. If you have an explanation for it, you get Nobel Prize. That's what the people did when they explained how type 1 and type 2 superconductors work. So what the higher temperature superconductors, they found that it instead of a singlet pair, like a Cooper pair, it's a triplet pair. So the
triple pair.
Triplet pair. So instead of electrons pairing up, one down, they found that the electrons are moving in triplets, triplet pairs, so they are both up or both down. So there's a correlation with potentially maybe even antiferromagnetic materials, or I'm just talking out of my ass here. But there's a lot of like correlations with magnetic properties and superconductivity.
Interesting.
Because these things, the reason they can levitate is because they don't want magnetic fields.
Yeah. Okay.
So they repel. They repel the magnetic field lines around them. That's why they can lock.
Yeah.
So if you can find a way to find that behavior in a specific given temperature, that can display something similar, or at least show that the electron behavior either pairs up in a singlet pair or a triplet pair, you can help discover superconducting materials.
Yeah, and I think so. I just read this description of a paper. It wasn't their paper, but Tej sent me this thing this morning or last night, and so because Monday we meet with my advisor at OU,
Samuel,
Dr. Bernard.
For the Samuel lab?
No, so actually, I was telling you about this. So Tej is wanting to collab with OU, but also keep furthering my research, and so he wants me to. He wants me to place me as a key personnel or key personal on this grant that he's applying for, and he's asking Dr. Bernard to also be a PI on the project. And so he sent me this paper because I need to get something written up to show Dr. Bernard sort of what our idea is, right, and what our research is. So give him sort of an overview of it on Monday, because we talked to him Wednesday, and he was like he seemed to be totally down to do a collaboration between OU and UCO, which was really awesome to hear.
So exciting.
Yeah, exactly. So, I won't just be tied still to Physics Society, but also possibly research as well. And this would give me hopefully an opportunity to hire undergrads as well to do this work. But so this paper or thing that he sent me this morning, they were using agents. They were using AI agents to sort of do the work. So they sort of set the experiment up, and then they tell the agent about this experiment, and the agent just reiterates trying to make the models better at predicting this property that they're wanting the models to predict for. And what they have the AI agent do is, once they have a run and check for the accuracy of the model, they then go and basically have the model the agent use DFT to create synthetic data.
The agents can use DFT.
Yeah.
I mean, I guess that makes sense.
Yeah, and so they make synthetic data based off of certain things that we know about materials and what materials will. They sort of just start to put materials together that I guess would make sense, and then they do the DFT on this to calculate for. I think it was the magnetic moment, if I remember right.
The coupling constant or just magnetic moment?
Yeah.
Coupling constant?
It was a coupling constant. Yeah, J, yeah. and then so they just keep making synthetic data, and the model keeps getting better. Now, if this it'd be interesting to see if this is actually able to be fruitful in the real world. Like, can they take that model, have candidates to go synthesize, and will these be like possible materials that have like those properties that they're predicting for, right? But that just opened my head. I was like, oh man, I could take what I'm doing now and sort of do something sort of the same, and then apply it to that property of superconductivity, possibly.
And you're learning about DFT from Teo anyways.
Yeah, exactly.
So, also on the last episode of our podcast, we talked about DFT.
Yeah.
So if you're interested, you should watch it. But yeah, I just looked it up. So type 1 superconductors is the very cold one, colder than liquid nitrogen, usually liquid helium. They are the conventional superconductors. They use the phonon-electron coupling. Phonons are the vibrations of the lattice, and electrons are electrons. Because of these phonons vibrating in specific ways, they're cold enough that the vibrations are now quantized, and the electrons move in phase with the phonons, causing the electrons to pair up, creating Cooper pairs. These Cooper pairs is what brings superconductivity.
Dude, that's sort of like what are those when the metronomes, you put metronomes on a table that's moving and they start to
synchronize?
up.
Yeah.
Like the resonant frequency?
Yeah. So synchronization. So in a way you can say that, but the temperature has to be cold enough.
Yeah.
So if you think about it,
it always kills my ideas that I think are cool, but whatever.
Yeah, because I'm just giving you an example. If you want to be when you have that one unified motion of that table, for example, on the metronomes, that is like assuming it's cold enough. If it's not cold, you're imagining the chaotic motion of the table. They cannot sync up. So type 2 superconductors is a mixed situation. The very cold type 2 superconductors seem to have some level of phonon and electron pairing, but they observe something else. So they on the higher end of the temperature, when they say high temperature superconductors, they're talking about anything above 77 Kelvin. So it's still very cold. So it's still liquid nitrogen temperature. It's still very cold, but they're considered high temperatures because it's higher than the type 1. They notice that magnetic fields don't completely avoid it. So it's an incomplete Meissner effect. This is called a complete Meissner effect, when magnetic field completely avoids it. In the type 2 situation, some magnetic fields to go through. So no one has an explanation for it. No one knows how the high temperature superconductivity works yet. If someone can model it and give us a explanation, or I guess equations to explain how this works, we can probably simulate it better, and DFT will probably help. But the problem is we don't even know how to describe it, so we can't put it in DFT yet. You get what I mean?
So you'd have to come up with some so like in the easy Monte Carlo simulations, right, or just in Monte Carlo simulations in general, there are different dynamics that you can use, right? So essentially this goes into like why an atom would flip from up or down, right? And so it's dependent on different probabilities and different ways that the system is coupled. So maybe it's just coming up with the right dynamics probability for that. atoms flipping.
Best models that they have right now that isn't confirmed, is still controversial because we cannot perfectly replicate it yet, is spin fluctuations. Sounds like an easy model.
Yeah.
So they believe that the magnetic fields of the entire atom is fluctuating. And that fluctuation is propagating through the material like a spin wave. You see where I'm going?
Yeah.
That spin wave helps propagate the electrons with it. So instead of just phonons help propagate the electrons, which is the type 1 conventional superconductor, the unconventional superconductors, people believe that is spin waves that help, or at least spin fluctuations of some sort, that helps carry the electrons and usher them through, creating superconductivity. But no one knows.
Spin waves.
Yeah, that's what I was just about to look up spin waves and magnons. So I wanted to visualize this. That's a 20-minute clip. So spin waves are real.
Oh no, these are AI content. Don't look at these. They miss. They are very very big.
Clickbait. Spin waves, the future of electronics.
I prefer these.
Oh. Okay.
Circular motion.
So this is just one type of spin wave. If you look for spin fluctuations, I guess, or magnons, that is what a magnon is, or spin wave. But spin fluctuations.
And then if there's a spin wave from the other direction and like it cancels it out, like what's?
That's a good question. We don't know.
Phase fluctuations. Looks like the easy model right there.
It does, right? So I don't think they have any animation for that, but basically just imagine when you warm up a lattice, the lattice will jiggle around, but also the magnetic poles will start flipping. You've seen the easing simulations. Some parts will start moving around, some parts will flip up and down, and those flipping up and down is spin fluctuations. And they say that the high temperature unconventional superconductors are probably ushered by quantization of these spin fluctuations.
They do a Mexican wave.
Sort of. So, but no one knows. No one knows specifically how it happens yet. No one's proven the model.
Interesting.
Yeah. So the type 1 superconductor is called the BCS model. It's when the Cooper pairs form because of phonons, but the type 2 superconductors, no one has a proper model yet. If you create a proper model that accurately predicts it, you get a Nobel Prize.
Interesting. This looks a lot like those magnetic vortices that Tej
these are
about
precessions. So the MRIs use the same effect.
I see.
So when you when you have a hydrogen atom in your body aligned with a strong magnetic field, and then you blast them with radio waves, they'll knock them over. And when they try to align back, they precess.
Yeah.
And that precession is how we see all the details on the human body, because at the precession they emit radio waves.
Interesting.
Ooh.
Yeah.
Tops are so like the physics they have are interesting.
Yes, seriously.
And like in space precession, how does it connect to space?
So in space, a precession comes from the fact that, for example, a planet has a tilt, right? In the presence of another larger object, it orbits, right? When it orbits, its axis usually stays the same. So the whole year round, it looks like it's precessing, but it depends on the frame of reference. If you're on on planet Earth, you're technically not precessing. Oh well, no. From the outside view, it's not precessing because the axis is always pointing the same direction when it goes around the planet. But on the Earth's perspective, Earth is precessing. So that's why we have seasonal changes.
Yeah.
So it also comes down to frame of reference.
Do you see where they could see the Borealis effect whenever they shot out of the Earth the other day?
Yeah.
Artemis 2.
Yeah, Artemis 2.
That'd be so cool.
Artemis 2, man. Would you guys want to become astronauts?
No.
Oh.
I mean, in the future, if it feels like it's safer.
If it's safe, yeah.
I mean,
What
Honestly,
about you?
I feel a little claustrophobic, and the bathroom situation would be a little rough for me.
Yeah. Oh, you're
The mental fortitude.
Yeah. Because imagine you're in space. You're in this spacecraft. You're 1 feet away from absolute nothing.
Yeah.
That 1 feet of special aluminum and tin alloy holding this entire and titanium holding this entire ship together. That 1 feet. Right outside that is nothing. It's vacuum.
Oh my goodness! What if you're an astronaut and you like mess up the module like you're in, and you risk everyone's life?
Yeah, that
the whole craft that everyone worked hard on.
Yeah. So if there's one small leak, the whole thing.
Yeah. Yeah, I mean, there was a lot of stuff coming out about some of the issues that they were having up there. And
to be fair, we haven't been out there in a long time.
Yeah, it's kind of wild.
At least that far off.
Well, and that's what's kind of crazy is that how expensive it still is, right? Like you would think, when did we land on the moon?
1969.
Yeah. Yes, 1969. Exactly. Yeah. You're right. That's my father's birthday.
And typically, things are supposed to get cheaper, right?
No,
but
it only gets cheaper if you do it all the time and you scale it. Mass produce it. But the problem is we don't have economy of scale for rockets. Yes, SpaceX did a lot of contributions. And it definitely, hopefully, saves more money this time because you instead of like blowing off rockets every time you use them, now you're reusing boosters.
Yeah.
So it's technically getting cheaper.
Yeah.
Way cheaper compared to before. I think back then it's like $20,000 per kilogram of cargo.
I wonder why it is we decided to back off the space program.
There's no need for it.
They achieved the goal.
Yes.
And it's too much money right now.
Exactly. Because a lot of back in the day, the only pressure you have for going to space is the not the Russians, Soviets, because of Cold War.
Yeah.
They have space. They can put weapons in space. They have satellites in space. We need to do that too. So we one up them.
We need to do that too.
Yeah. So we one up them. I'm not even American, but I guess we in America. And then we did a spacewalk and we landed on the moon. We're telling them, hey, we got it. And at the time, they probably don't care because they're already bankrupt. But at least we show that, hey, we landed on the moon. Yeah. But after we came back, we realized how risky it is. Space dust is toxic. Space dust is deadly. If you didn't know, space dust is sharp, like the moon dust, the regolith. It's sharp because there's no air and water. So nothing is smoothing out the dust particles. So every impact.
There's no winds to
there's no atmosphere.
Not on the moon.
So that's why all the dust that you see stick on the suit. A lot of the astronauts could develop breathing problems later on in their life because all those dust particles are microscopic knives.
Apparently, it has a certain smell too.
They smell like steak.
Steak.
Yeah.
Okay.
So
I would love the moon then. All right, astronauts, sign me up.
You need to be part of the Air Force first.
Yeah. Well, I mean, that's what Levi wants to do.
Wanted to do. He says he's reconsidering because now he has a child.
Well, some of them have kids.
Let the man be. He's speed running his life here. Okay, let him take his time to slow down. So, what was I saying? Oh yeah.
You want to be an astronaut?
No. I'm talking about the reason why we don't do it anymore. Because it's dangerous, it's toxic, and people are more. The industry just started booming. Economy just started getting better. The war just ended. Everyone's celebrating. We reach peaceful times. And now we're confident that we can put a lot of objects in space and we don't need anything more in space. So we already have a floating space lab, the space station. What else do we need?
Isn't that kind of...
At least at the time.
I don't want to get political or whatever here, but isn't that kind of wild though that like a lot of our innovation comes from warfare, military.
And a lot of money if you're selling the weapons.
Yeah, like the project I'm going to be on, right, is it's backed by the Tinker and the military, right, and it's
the radar.
It's going to be $100 million project.
Oh yeah,
possibly more.
Yeah,
which is wild. $100 million.
You have to also realize, I think it's mainly in the United States because the defense budget. But in a lot of countries that do also innovate, for probably the most of the money probably does not come from the defense budget, because here one of the highest budget in the government is the defense budget. So it makes sense that the defense budget has the ability to invest in research. And if you, again, necessity is the mother of invention, right? At the time of war, you need all this stuff.
Yeah.
Astronomy led to NMR led to the MRI. You see what I mean? So all these innovations, one led to another. You don't have to have war for innovation, but war at some point was a good reason to innovate. But not anymore. Hopefully we have the reason to innovate without war.
Yeah.
That's the hope, that's the dream.
Indeed.
Yeah.
Like space gives a lot of reasons to innovate.
Yeah. Agricultural revolution.
Whole environment.
Yeah. Agricultural revolution and does not need war. In fact, it's at least back in the day, it was to solve the need for hunting and gathering. You can now grow food. Population boomed, and then people got bored and they started going to war again. But for land,
they got bored. I think we need to solve boredom. But we need problems to solve boredom.
And
boredom is a problem.
Well, isn't that what Instagram's for?
I get bored of Instagram. I mean, I don't use Instagram that much, but I get bored of the media I use.
Okay, that's one interesting thing I just wanted to bring up is that don't you guys realize the word romantic, from the Romance period?
Romance.
Well, more like the Romance period is because they talk about love a lot, right? But if you don't realize, the reason they talk about love so much is if you look at the literature back in the day, most of the romantic stuff is tragic because either they're forced to be married to someone for economic or political reasons, or they still recording?
Yep.
Okay. Or they ended up dying because back in the day life expectancy was not that great.
Yeah.
So most of the time they're forced to marry someone they don't even love or like. That's why most of the romance literature back then talks about their love life outside of marriage. That's why there used to be a saying. I don't know if it still goes around. It's like don't let your wife stop you from looking for your love of your life. So it's. But if you think about it, what a privilege we have today to marry the people we love.
Yeah, for sure.
Honestly, if they had a short life. I mean, it's more about money and like who has the money for like your future living. Like women's depended on the men,
and also men depended on they married that rich family's daughter so that the two big families can work together. It's for business reasons
improve
or political.
Prosperity.
Exactly. That's also why a lot of the royal family in Europe back in the day have very high incest rates.
Yeah.
So, a lot high inbreeding.
Well, I mean, a lot of people say, marriage. You should get married because of some of the tax incentives, but there's not really a lot of tax incentives in.
I mean,
maybe a little bit, but
I mean, for example, let's say in Korea and Japan, they put out a state of emergency. One of them. To the United Nations because of that population crisis. Because birth rate,
I've heard about this.
Birth rate index went below 1. It's an index. It's not supposed to go below 1. But it's so they are clearly in danger for their population. So they're now trying to incentivize people to have a family and have kids.
Yeah.
But it's too expensive. At least to a lot of people. A lot of people nowadays think that having children is a luxury.
I hear that, right? And I get it too. But, like my parents, right? They just wanted kids. They didn't care about
how expensive
it was going to be. They were just of the idea that we'll get through this, right? I don't think people who really want to have kids think about how much it's going to be.
No, it's true. It's just interesting how you see the idea of romance and relationship evolve over time.
Yeah, for
culturally,
sure.
Politically,
and
then you have like some countries that like even though they are not doing economically well, they have like 8 kids.
Yeah. religious beliefs. Also in the past, like if you had more kids, they can work the land, they can have jobs. So like they'll pay off eventually. Like, and if you have enough of them, like the older siblings raise the younger ones too.
Yeah.
Because at least that happened in my mom's family.
And I notice a lot of young couples nowadays that are young, newly married couples. They don't have kids, they have pets, and they call that pets their kids because they don't plan to have kids.
Yeah, that's me for sure.
Yeah.
You got a big family.
Yeah, we got 6 animals.
That's a big family.
Yeah.
6 kids.
Well, and I don't know really how to think about this. There was a point in my life where I thought, oh, well, the population is too large, we don't need to be having kids. But, then there are some people that say that, that you have to have a certain amount of birth rate in order to sustain a population, right? But, and so I see why, certain societies, civilization, like you said, Japan, right, was telling
South Korea as well.
South Korea trying to get people to have kids and get married and things like that. But
because if you think about it,
is like what is the do we need to have is the population just going to collapse if we don't have a certain amount of birth rate?
A certain threshold, it will collapse. The reason why
because I guess you're worried about age too.
Yes.
The age of the population
proportion is what they care.
But we have 8 billion people on Earth. Can it collapse that fast?
No, we're not talking about the global population. I hope there's no global population collapse.
Some people are caring about global population.
Now, you have to realize South Korea and Japan are announcing at some point a state of emergency for their own country. Because, yes, globally probably is never going to collapse, but unless there's a nuclear war. But if you have your own country, let's say by in next 40 years, 70% of your country will be old people.
Yeah.
They have to retire eventually. And then once those old people die, all the pension they used up, who's going to fund the governments by taxes? The young ones. But the young ones, that means you now only have 30 to 40% of the active independent population. The rest of the 60 to 70% is dependent population.
So this gets into something interesting. So then, like, are we as our governments overspending, right? Because are we overspending? And it seems like we're, especially in like a capitalist society, right? It seems like we're investing in the future, right? So we're really overspending, betting on the future, essentially betting that our population is going to keep growing.
That's what happened to Florida.
And so, is this really? It seems like I don't know. It seems like that would just lead to disaster, right? That leads to.
It's not leading to disaster if you know what you're doing. For example, back in Florida,
do governments know what they're doing?
So anyways, at some point they used to have a saying, philosophers should be kings, because philosophers think about stuff, at least back in the day, because back in the day they don't have scientists, they're philosophers. Right. Modern day, I feel like I don't think scientists should be kings, but I think at least people who are well versed in STEM, in both the social sciences and natural sciences, should be leaders.
The council.
Not kings. So you were saying kings there for a second.
No.
I say maybe I can see a robe and a
no. We don't need a pope. We don't need a king.
We need a council.
Exactly. Yeah. We need a council of literate scientists, engineers that are trying to build a better world through knowledge. But that's a topic for another day. But I think the main problem now is. People betting in the future is normal, because let's say you're saving money. Why? Because you know in the future you may need it, or your girlfriend may need it, or your family may need it. You're already betting the future even if you're not spending it, because you're betting
your child may need it.
Yes, or your future 6 kids. 6 animal kids may need it. So,
a lot of vet visits.
And at some point in Florida, they expected Florida's population to skyrocket because they were doing so well. In fact, they had so many car production there, to a point where remember at some point recently, the last few years, car prices dropped so drastically. You can buy very, very cheap cars from Florida.
Yeah, I think COVID hit.
Especially then. Yeah. So that's because they bet in the future. They thought population is gonna rise in Florida, and then suddenly it stopped.
Mm-hmm.
But now the bigger question is, right now, since population crisis is happening in a lot of developed countries, and there's a trend. If a family doesn't, at least in every 1,000 people, they should have at least each family should have at least 2 kids to keep the population roughly the same. So because you have 2 parents, 2 kids, 2 parents, 2 kids, that will keep the population roughly in equilibrium.
Yeah.
But if you have a surplus, well, population rise. If you anything below that, like let's say you only have 1 kid, or in some statistics half a kid, that means for 1,000 people, only like 500 is having children.
What does half a kid mean?
Half a kid, so 1,000 women, only 500 is giving birth.
Oh.
So
I could see the future where you like
statistically, 1 woman only have 1.
You like pay somebody to have the kid for you.
Yeah, no, people already do that now.
Oh, well,
surrogate mothers.
Yeah, I know what you mean, but I'm saying, like, what if you had a quota, right? What if you had to personally have like 2 kids, right? And you're like, well, I don't really want kids, so I'll pay somebody to have the kids.
I bet the robot.
I guess it's in a weird. I guess in a weird way, right? China used to have a 1-child policy, and that sort of
led to some issues.
Some issues in population and demographics. But when you look into the future, if there are countries like South Korea and Japan, I'm not saying they'll do that. I'm just saying if you want to maintain a natural population about at least about a specific equilibrium, do they need to start incentivizing like a 2-child policy? Like, hey, come on, at least have 2 kids. You know what I mean? Like, what do they do? You know, what can you do? Because right now what they're doing is they're paying people. If you have 1 kid, they'll pay you like 10,000.
Yeah.
But what's 10,000 gonna do? A kid's way more expensive than that. You know what I'm saying? So it's like,
yeah, I think it's all about the right incentives, and it
social engineering.
Seems like money isn't really a good incentive. It is, right, in some situations, but I think that, like, for instance,
logically, would you go for a kid for $10,000?
No,
I can't even pay my school fees with $10,000.
Maybe if they're saying like $1 million,
his school fees.
Maybe if they're saying like $1 million or something.
Okay, I'm down. Like, I have 5 kids if it's $1 million.
Go.
That's great.
Yeah.
But will governments want to spend on that?
Well, no,
exactly.
Because then everybody's a millionaire, and then that changes the hierarchy and the economic ladder.
We don't even have enough money to fund an entire population to have like 2 kids each. We don't have that capability.
Well, that gets into, not every country can be in America, right? Like, which is kind of wild to think about. That, they're almost so
yeah, that's one
resources. We go through so many resources in America. And if every country was going through the amount of resources that we go through, we would use up our resources on this earth a lot faster.
That's also why a lot of countries have reserves.
Yeah. But, there
oil reserves, natural reserves.
And that gets us back to, something that we've talked about a lot this semester, which is sustainability and yin and yang, right?
Balance.
A balance. There's this weird balance that just almost overpowers everything else in the universe.
If the real question is, if we don't, we'll die. So, but I feel like, let's assume every country somehow overnight became a capitalist country, okay, or at least at minimum a social capitalist country. Every country will start consuming a lot because their people starts having better education, more spending power. The problem is the rate of consumption and also the rate of production. Can we keep up? This is an economic problem. Can we keep up with the demand, the supply and demand? But now, can we supply sustainably?
Yeah.
We can't. Because a lot of stuff we use, like plastic, metals, we do not recycle them.
Yeah.
Yeah.
All of that's
from petroleum. Harvested.
And that's what's
synthetic
wild
plastic.
too, right? Like, so have you guys ever been to the dump?
Yeah, landfills. I've never been there, but I've seen research on landfills is getting crazy.
You know, me and my girlfriend, we just recently put up our lake house for sale, right? And so there was a lot of things that we needed to throw away, right? That, you know, just we don't need anymore. And, you know, because we had 2 houses, we have like 2 everything, and we don't really need a lot of the extra things. And you know, a lot of it was just trash. It wasn't like things that are useful. A lot of we took the useful things to like the Goodwill and whatever, but we did end up throwing a lot of stuff away, and we took it to the landfill. And you can just pay $50, or if you live in that county where the landfill is, you can just go dump it for free. And so you can literally take like a truckload of stuff, put it on top of this huge hill
of
trash, and then a guy comes over at the end of the day and smooths out all the trash and puts dirt over it. I'm just like, a lot of that stuff you could see could easily or should be recycled.
Now my question is how?
Yeah. Right. Yeah, because it's a lot, right, to deal with.
Not only that.
You could create jobs. I don't know.
The problem is we don't have a sustainable way to recycle yet. Because even recycling costs money.
Yeah.
And who's gonna spend money on recycling stuff?
Yeah, I don't know. Yeah, and
government should.
Exactly. Exactly.
They should incentivize that.
And honestly, you know, one of the things that you notice when you're at a landfill is how bad it smells, how bad the conditions are there. Exactly. So you may be able to pay people to go and do that, but I mean, is it a sustainable job? It is. I mean,
it's not healthy.
Not healthy.
Both for the environment and
for the people's
health. And not only that, you're wasting a lot of resources. Okay, I have an interesting question for you, right? Because biological systems love to adapt. We already know that there are bacteria already consuming plastic. Now, do you think that we should make more or better plastic-eating bacteria to, let's say, go to the landfills, just pour it in there, they decompose the plastic back into organic materials, because most of them can become organic materials because they're all hydrocarbons, just different with extra steps. So do you think we should do that? Releasing synthetic bacteria that is plastic eating.
I think it's dangerous because...
But naturally they already happen. They already discovered bacteria that can.
If they get really good at it, it could be not good. But I don't know, maybe they should have like a facility where they have those bacteria that eat plastic. You feed it in that facility so the bacteria doesn't leave it. It lives there. And it consumes the plastic, makes it, you know, recycles it, and gets rid of the toxicity. I think that would be a way forward.
What is the byproduct of that?
A lot of organic materials.
Really?
Yeah. So they so depending on the type of plastic you have, they break. You can search it up. So plastic digest plastic eating bacteria or something.
If they like reduce the toxicity.
I don't know if they do though.
Yeah, I think that still needs to be improved.
Yeah, they turn it into those two things. And then they somehow use that to generate energy.
Ethyl glycol.
That's used a lot.
Acid.
Yeah.
Huh. Yeah, I don't know.
I can see how ethylene glycols turn into energy. I can see that.
So
that can easily go into the Krebs cycle.
Well, have you seen the guy who was turning plastic into fuel? Oh, okay, yeah.
Again, I think that's a great thing they're doing, but is it profitable? Because companies will not invest.
Of course, it's not. But this guy.
Yeah.
Oh, that's a cool title.
I made my own gas station using plastic as fuel.
Why is this not a
battery?
Oh.
Battery full.
Well, we use petroleum to make plastic. Why not the other way around?
Yeah.
So I've created my own gas station that makes fuel from plastic waste. Let's go.
Man. That is so cool.
Yeah, I'll show you a video where he fills up a truck with it, and it runs just fine.
Bro's a mad scientist.
He really is.
I bet the comments like this guy is sane, this guy is well, because you know.
Yeah. He's not suicidal.
Not suicidal. He's happy with his life.
No, he's apparently had some security issues and health issues because of possible.
This here is plastiline. Gasoline I made from plastic waste. We are going to put it inside of this.
Plastiline.
It's indeed in there. Yes, indeed. So I've created my own gas station.
So
I want to see it working
there's
with it.
videos of this guy. Plastiline. Where does he fill up the truck? Is it? Yeah, here. Let me just look up.
And I wonder, like, that doesn't damage trucks.
My question is, how pure does the plastic have to be? Do you get what I'm trying to say?
Yeah.
You saw he was putting in all kinds of crap in there.
That's my point. So how often does he, like?
I got Julian here, the inventor of plastiline. This is gasoline that used to be plastic, and he made this. So we had him out, and we're trying it in our truck right now.
Well, because we know that plastics are made from oil, right? Which is Petroleum, yeah. Which
is oil.
Yeah. Crude oil. And we will see it, suck it up. Go ahead, start it up. Oh, it's already going. Oh, it's going in. Oh, it's pulling the whole bottle. Oh, yeah. Oh, Jesus. It's going here soon.
I mean, I don't know what the gas mileage on it is but.
No. My question is, how does he make it so that it refines to one specific hydrocarbon? Do you get what I mean? Because you're randomly breaking bonds. How do you make sure it all becomes octane, for example?
Let's turn some plastic into fuel.
I think this is. Oh, okay.
This is plastic crude oil. And as you can see, we have quite a bit of this plastic crude oil. We need to refine it and clean it up.
It's going to become a lot clearer.
I see. So he used fractional distillation. Yeah, he uses fractional distillation to
After
clear.
some time of the refiner being on, well, that plastic crude oil turns into...
Bro has this on his backyard. Can you believe that?
Yeah, dude. It's wild.
And I wonder how much plastic produces how much.
Yeah, that'd be interesting to know too.
I guess that amount for the whole baggy stuff.
And what about the leftover byproducts? Where did they go?
Yeah.
Like all the chemical byproducts.
Yeah, I don't know.
Gases.
Yeah, interesting though. And you know, there's also a lot of like, you know, not to get conspiratorial or anything, but there's, you know, conspiracies that they created like cold fusion a long time ago, and that allegedly these guys who
assassinated them.
Yeah.
I don't know about that. In my opinion, like the real conspiracy is clearly just lobbying. Like for example, we've talked about why we don't have bullet trains in America. And that's because this is a country of cars and oil, using a public transport system that can usher in large amounts of people, both rich and poor, will be very sustainable, very energy efficient. But that means they use less fuel.
Yeah, energy and money is kind of a interesting
commodity.
Yeah.
So if you want to have public transport system in America that is good, you need to find a way to decouple the economy from oil.
Which is going to be really hard to do because these oil companies are so huge, right? And make so much money.
Yeah.
It's like, why would you, as a company, want to make less money? I mean, of course, you know, and apparently energy companies are doing things to, invest more into sustainable alternatives and things like that. But, we've talked about it before, right? The grid is also a big issue in this area, in this topic, right? Which our grid isn't good at using sustainable energy resources. It's a very crude system. There's, I don't know if you've heard this, Anjali, but so like windmills, for instance, you have those windmill farms, right? And not every day is a windy day. Like solar panels, not every day is a sunny day. So on those days that's not very windy or sunny, you don't get a lot of energy. So you have to supply energy from somewhere else, right? And then also there's times where it's really sunny or it's really windy, and sometimes that's
surplus in energy generation.
Surplus, and you have to
divert the electricity somewhere.
Yeah, which apparently, and I was listening to Jensen Huang, yeah, the NVIDIA CEO.
Jensen Huang.
He was talking on the Lex Friedman podcast about trying to use some of the excess energy that comes off of our grid to be able to supply these data centers.
Because if you didn't know, in places without any what they call industrial batteries, either they store it in the form of heat or they store it in the form of gravity, like water pumps and all that. Those excess electricity just goes to the ground. They're wasted.
Yeah.
Well, I actually thought they stored it in a better way.
No, there's no industrial battery big enough to store such a large excess, and there's not enough, and the battery's output is not big enough of a voltage to supply a deficit of that scale. We don't have something that can do that consistently.
Yeah, so, I would like to dig more into this because, a lot of people right now are under the assumption or under the understanding that data centers are going to take a lot of the energy, make our energy prices go up, but also at the same time, we produce excess energy. So
sometimes.
Yeah, sometimes.
Keep in mind, a large amount of energy in north side of United States comes from Canada.
Interesting. Probably hydro. I think we get a lot of hydro from Canada.
Hydroelectric is the most efficient energy generation.
Yeah, which is kind of scary that a lot of our rivers and things and lakes are like starting to dry up. Which is, but the topic of energy and sustainability is really interesting because, people make it political and whatever, but
if you have unlimited energy, think about it. If you have unlimited energy, you can do anything. Travel anywhere.
Work.
Yeah, machines can operate longer, right? Energy is literally the most expensive thing right now. That's why oil is expensive. It's because oil is the hallmark of energy storage. It's purely energy stored in a bottle.
Yeah, and I don't know why it makes me nervous, but it makes me nervous thinking about how much sort of fuel a spaceship uses. It's like thousands of gallons of fuel.
But they usually use their own synthetic fuel. By synthetic, I mean like they specially curated ones. So like they use hydrogen and oxygen combination or oxygen and methane, but they specially curated it. So
yeah, I'm just still kind of.
If energy is like conserved and you have a spaceship leaving Earth, like is that energy is like leaving Earth, right? That's still in the universe.
Yeah, but entropy.
Heat.
Yes, entropy is taking it away as waste heat, and when the spaceship is coming back down, re-entry friction, air friction will.
Well, then Professor Prather, actually, let's pull it up because I thought it was so freaking cool. So let's go to Professor Prather's website, pyrestes.com.
I've seen this website today.
You saw it today?
Well, no, I saw it when he linked it in the Discord.
Oh, okay, yeah. So this right here. So this is his simulation of the of Artemis 2. So you can, let's see here. I think you can restart it. Yeah, you restart it.
Press play.
And press play.
They're coming back today.
Yeah. And so you can speed this thing up. So you can see, and even right here, vroom,
that is the gravitational assistance.
Yeah.
Or gravitational slingshot.
And then here comes the moon. I thought it was so cool he put this together.
Yeah. I didn't know the moon was like meeting
and the moon pulls it back, so they didn't even have to, because they thought that they were going to have to use thrusters in order to basically turn around, but the moon actually provided enough gravitational pull to pull them back to where they wanted to go.
Gravitational assists.
Yeah.
That's why if you're working at NASA, some of the jobs is just purely astrodynamics. So calculating orbits, trajectories to minimize fuel consumption.
Yeah, so I think, so he even has like a live thing that shows exactly where they are. And he said it's off by like a couple minutes or something like that.
That's
a couple of, and so he was saying that his simulation was off by about like 10 days or something like that. And one of the reasons was because he didn't account for the sun's. I forget exactly what it was. He said that it was off by, but essentially his simulation was off. And the reason for it is because he didn't take into consideration the sun's gravitational pull that was going to be had on, I think, either the Earth or the Artemis 2. And so he added that, and now he has this like pretty accurate simulation. Yeah.
Just imagine the Orion people on board. They're just literally flying by the moons, looking back at Earth.
So cool.
Right?
Well, yeah, they had that shot where they have the moon and the Earth in the same... so
the same
cool.
view.
Yeah. Yeah, the space is... no, I don't think I would ever be an astronaut. I would totally go into space if it was safe, right? But to me... and I know we've talked about this a lot, but space to me just is so fascinating, right? Apparently, there's more planets than there are seconds past the Big Bang. Have you heard of that?
I mean, I don't doubt that because if you think about it...
Which is kind of wild and it feels counterintuitive.
No, it makes sense.
Makes sense to this guy.
No. Look. If you have hundreds of billions of galaxies...
Explain it to us, Albert.
Hundreds of billions of galaxies, right? Mm-hmm. Each galaxy has tens of billions of stars. Each star has at least 1 to 9.
But my thought...
Why is it a limit like that?
Huh?
Like 1 to 9.
Well, with the best. So if you notice, if you look at if you look at the number of exoplanets we've discovered, right? Exoplanets, exo just means outside, planet it's any planet outside of our solar system. If you look at any exoplanet we've discovered using either James Webb or Kepler or whatever, you've noticed that they only discovered giants. Do you know why?
Because they're easier to see? I don't know.
Exactly. They block out the sun easier. At least they block out the star that they're orbiting easier. That's the main way we discover planets. By how much a planet blocks out their sun. We cannot detect anything smaller than those sizes. So those planets on average are at least twice the mass of Earth. At least. And usually they are the size of Jupiter and Uranus and all that. They're huge giants. So we haven't taken into consideration the small rocky ones. Mars, Earth, Venus-sized planets. We haven't taken into consideration. And here's the crazy part. Life most likely is going to happen in those sizes.
Yeah. Not
the giants. Because giants are too chaotic, too geologically active. Pressure's too high. We don't know. Well, we don't know. The only sample size we have is
too much gravity.
Too much.
Well, yeah. We only know of the life that we see here.
So based on that, we only discovered the big ones. We have not discovered the small ones. Wow. So we don't know the actual limit or the average amount of planets a solar system can have or a star system can have. But based on our estimates,
I guess why it feels counterintuitive to me, because I would think, okay, well, you need some time to go by for the planets to actually form.
Well, what they mean?
But yeah, go ahead.
So let's calculate the amount of seconds the universe has.
Okay.
Right?
How many seconds is it supposed to be?
So 13.8 times 10 to the power of 9. That's years. So times 365 times 24 times 3600. Right? Correct. So that's 4.35 times 10 to the power of 17 seconds. Oh wait. So what was?
That's gonna be more than that.
What's the saying?
There is more planets than there is seconds past the Big Bang.
Okay, so assume we have 4.4 times 10 to the power 17 seconds. That's a fuck ton of seconds. Okay. Now, let's say we have 100 billion, right? 100 billion. Search how many galaxies that we know of from estimation. How many galaxies are there? How many galaxies are there? And just search how many galaxies are in the observable universe.
Oh my god.
And then I will search how many stars are in a galaxy on average. So what does it say?
It says I think.
So so average is 10 to 100 billion stars. That should be 100 billion.
10 to 100 billion
stars per galaxy.
Wow.
So that is anywhere from 100 billion to 2 trillion galaxies.
Wow.
Now let's take the in between, shall we? So 2 times 10 to the power of 12 plus 10 to the power of what is 100 billion? So that's like 11. Right? Yeah, 11 divided by 2, so the average is that. So now we'll take the average of that, 10 to 100 billion stars. So let's take the low end, 10 billion. So times 10 to the power of 9 stars. Now each stars would have how many planets?
Each star? 9?
Huh? So like at least one.
Okay.
So let's take the average. Okay. Let's the number of exoplanets per galaxy on average is probably like, let's switch it up to be more accurate. How many planets per star system? Per star on average is 1 to 2, but they are all big ones. That's the one we find. So okay, let's just assume 1 to 2. Okay, let's just take the one. Let's take the observed amount, because these are again, we only observe the big ones.
Dang, then why do we only have 9? Or why do we have 9 then?
No, because we have dwarf planets. Well, if we're not counting dwarf planets, only 8, and 8 includes rocky planets. Again, most exoplanets we see are giants.
Yeah.
So
but then
so look at only the giants on the solar system. How many giants do we have? 2 to 3. Jupiter, Saturn, Uranus.
About 1
Neptune, I guess, if you want. But these 4 giants, but Neptune and Uranus are already difficult for us to spot. It took us hundreds of years to find it. So we probably only discovered the Saturn or Jupiter of those star systems. So now, keep in mind, this is only 1 to 2 on average that we spot in distant stars. So let's just times 1 to 2, so 1.5. So 1.5, 1.5. 1.5 times 10 to the power 21 planets.
Yeah.
Remember, this is not how many seconds do we have. 4.4 times 10 to the power 17. And now we have to the power of 21.
Boy.
So we have orders of magnitude of 4.
4, yeah.
So we have.
You're saying we have more.
We have 10,000. We have 10,000 times more planets than there are seconds in the universe after the Big Bang.
That's so crazy.
And here's the best part: this is only in the observable universe, not the outside of the Hubble horizon.
Which is insane to think about. That this, all the stars that we see are not even close to the amount of stars in the universe.
Yeah, and here's the best part: the stars that we see with space telescopes are not stars. The stars that we see in space telescopes are entire galaxies. You have
That
to.
is the craziest thing.
Yeah. So the most of the lights you see in the night sky are galaxies.
There's got to be aliens, man.
And here's the best part. This amount of planets is only in the observable universe. So and the observable universe is 96 billion light years across in terms of diameter, in volume.
So then we're basically saying that there could be even a lot more.
Yeah, that's just the observable part.
Yeah, so
the non-observable. Here's the best part. We through sky surveys.
So then does that make you think that the universe is probably a lot older than what we think it is?
Again, okay. Here's what people misunderstand about the age of the universe. People be like, "Oh, time started at the Big Bang." No, our equations started working at the Big Bang.
Yeah.
Again, the Big Bang isn't creation. The Big Bang was the beginning of understanding based on our models. For all we know, the universe could be infinite of age. It could be cyclic, you know.
Yeah.
And again, based on our best model estimates of spatial curvature, we've determined that the universe is probably flat. By flat, I mean no curvature, so therefore it's open universe. What we mean by open universe is that it's most likely infinite. So yeah, so if you that's what we mean by flat. Of course, there will be a flat universe people out there now, but yeah. So,
man,
this spatial geometry. Yeah.
So crazy.
So yeah, so
Anjali, I'm really go ahead.
Well, I was gonna say, like in math, when they look at different shapes, like Mobius strips, curves, inwards, and like circles.
Yes.
They've been doing like different experiments, and they've determined it's planar kind of.
Yeah. So how they do that is So how they do that is they use sky surveys to see if there are stars that pop up in two places at once. If there are stars that pop up in two places at once, there is. That effect is what we call gravitational lensing. So it makes the illusion that there's the same star in two different places because gravity bends the light. So let's say you have one star, the light goes two different ways, but as it's traveling this way, that's gravitational source here, it starts pointing back towards you. So in your perspective, you see two of the same star. So they're trying to look for, is there any signs of curvature in the universe at large? Not local curvature, global curvature. And based on the best results that we have, the universe is flat. So as long as you shoot two parallel photons, it most likely, as long as it doesn't bump into anything, it will stay parallel. That's what we mean by the universe is flat. Because if the universe is curved, if it's hyperbolic, two parallel lines will diverge. If it's positive curvature, parallel lines converge. Based on our best estimates and measurements, it stays parallel. So the universe, with our best models, is infinite.
Wow.
Insane.
Yeah.
There's an infinite amount of planets.
As far as we know, maybe. Because we're assuming, this is based on the assumption that outside of the observable universe should only be more universe. Just more of the same thing we see now. It's just more.
Yeah, we just can't tell.
Yeah, more galactic filaments, more galaxies, more planets. It's just we couldn't tell because it's too far away.
Yeah, that's wild. So, Anjali, what is the thing that pulls you to industry and want to go to do industry instead of continuing research? And
I feel like industry has like already knowledge that they've learned. Or research, you have to like
go to the cutting edge.
Yeah, you have to. It requires more thinking. I don't know. Like I'm still kind of undecided if I want to stay in research too when I graduate, but I kind of want to get an industry job for that reason because they would be able to train on things that they already know very well. And also like improving the problems there, but I don't know still. Because research with like doing stuff with biomimicry, in engineering capacity would be something I'm interested in.
So have you thought about looking into, since you're fine with going to a different state, have you thought about, just looking up, like, what is the university that is doing the most biomimicry of engineering?
I haven't thought about the university yet. I've only looked at companies, but also that was a while back. I haven't been looking at all recently.
You're just trying to survive, trying to graduate.
Yeah, I've kind of been there.
Yeah. I hear that for sure. Yeah, I just ask because you seem very curious, right? And so to me, it seems like a curious person would want to keep doing research, right? But we all have our reasons for doing what we want, right? So
I think if I'm a worm, I'm burrowing, but I don't really have a sense of where I'm going. Worms have a better sense of direction that there's water coming, I'm not going that way, or food's this way. Somehow they could detect. I'm probably a blind worm. I just go where.
Most worms are blind.
Yeah. I mean, so I think that's kind of a good way to think about it. For me, I just sort of try to let life lead me where it leads me, right? It's kind of wild, right? Because I really wasn't thinking about really my future, right? I know I wanted to try to keep doing research. I just didn't really have a good idea of how I was going to do that, where I was going to do that, or what. And then this semester I was like, okay, I got to figure this out. And, it's my last semester, so I'm like, and I just kind of got lucky, and I went and, talked to the right people at OU and ended up in this position now that, I'm, I got accepted at OU and got an RA position. So, I think you're doing the right thing in putting in the work, right? Because I think that's what's going to allow you to land whatever position pretty easily, right? Because you're going to have a lot of things to be able to go to somebody who, in an interview, and you're going to be able to say, I've worked on all these different things, right? And so you're going to them, you're going to be like the, I want to say the sort of candidate they're looking for, right? Someone who's curious, someone who's been putting in the work, right? So yeah, it's funny because I know that I like to ask you this question a lot because I'm very curious in what you want to do, but
I don't know. I'm the same type as you. Life will lead me.
I'll
flow wherever it's not just easiest to flow, but the direction I want to go.
Yeah.
But the more fun, challenging direction. That's where I want to be.
Heck yeah. Yeah.
I don't want something that's too easy or something that's not as satisfying. If it's challenging, that's good. Yeah,
and I'm excited that you're okay with leaving Oklahoma, because for me, this is home to me. I wanted to stay in Oklahoma, right? Maybe down the road when things are
postdoc, maybe
a little bit different, for me. Maybe moving out of the state is something I'd want to do, but at this moment, I'm like, I just love Oklahoma, and Oklahoma's providing for me, so I'm like, let's do it.
Oklahoma's growing a lot right now. They're going to have the Olympics in 2028.
Yeah.
2 of the events.
Well, Summer Olympics is going to be this summer.
Yeah. The World Championship.
Oh yeah. I think it's right. Rowing.
I think it's the actual the Summer Olympics, right? It's So it's
this year.
Softball and rowing is going to be here and we looked up tickets, $500.
Wait, I thought this was 2028.
No, 2026 this summer. Yeah.
Wait, this summer?
Yeah, this summer.
Okay, it's not Los Angeles.
Well, there are some events in Los Angeles.
That's in 2028.
No, it's in 2026. Yeah, there's
It's 28.
Yeah.
What, really?
It's 28.
Yes.
Softball, yeah, it's 2028. It's Summer Olympics 2028.
This is the cheap price.
It's an official sub-site.
Oh, so then maybe we're just trying.
There's a rowing one for the World Championships to qualify for the 2028 ones, I believe.
Oh, okay. Okay, well, I totally misunderstood that.
Because the Summer Olympics of 2028 is in LA.
Okay.
It's just that Oklahoma is a sub-site for hosting rowing and softball.
Apparently the last U.S. hosted Olympics was in 1996.
Okay. Anjali knows her Olympic history over here.
I just know I don't. I just thought
Also, do you guys realize, isn't it interesting that the space station is actually in the atmosphere?
Yeah.
It's in the atmosphere.
Yeah.
It's in the thermosphere.
Mm-hmm.
The same International Space Station is in the thermosphere, which is the layer of atmosphere where the aurora borealis happens.
You would
I
think
did not know that.
Yeah, you would think that they would get some some drag, but interference.
To be fair, the thermosphere is very big.
Okay.
Thermosphere is like 80 to 80 to 700 kilometers up. So they're probably in the higher end, and the borealis is on the lower end.
So you see it below them.
Right below them. So
I wonder if when you're on there, if it looks like you're going across the Earth fast, or if it just feels like you're just barely moving.
In space?
Like when you're on the space station, right? I wonder.
You feel like you're not moving. You feel like because you're in free fall.
Yeah, that's right. That's right.
And that's also why every now and then the International Space Station needs to use its boosters because it is slowing down because of air friction.
So then they have to transport fuel up there then.
I don't know how it works.
Yeah.
I don't know how they refuel it.
Interesting. So, y'all, it's 3:00. Time to wrap this bad boy up.
Oh, snap.
Yeah. Was there anything else you wanted to talk about, Anjali, before we get out of here?
No, I actually have a question for you.
Okay.
So if you do get your PhD, is it still going to be in material science or more biomimicry?
I want to go biomimicry.
Okay.
Closer there.
So
biophysics would be really cool. But I need research this.
Would you be interested in more of synthetic biology, where we try to create completely synthetic life, or is it just engineering, but trying to mimic animal features?
I want to do engineering.
Okay.
I don't want to be someone who does a Frankenstein. That's good, but I just don't want to. I don't like the ethical dilemmas in that.
I see. That's fair.
Mm-hmm.
That's completely fair. Wow.
Yeah, makes sense.
So what is the main biomimicry stuff that interests you the most? The main one. Because we talked about so many. We talked about hexapods. We talked about the biosensors, human hands, artificial eyes, tissue engineering, self-healing materials. Which part of biomimicry interests you the most? Because it's so big. It's such a diverse field.
Yeah. I think things that can move like animals can. Like their transportation. So the aerofoil for the train.
The
shape
beak.
of it.
The beak.
Yeah.
Well, yeah, and then there's have you guys seen Dune? Where they have those
ornithopters.
dragon
Ornithopters.
Yeah.
Technically, they're not ornithopters because ornithopters inspired by birds. Those are technically dragonflies.
Yeah. I love the sound. And there's a new Dune coming out.
Dune 3, yeah.
Wow.
Yeah.
Yeah, I think it's humans, we're limited by our physical bodies, but when we can go past that and we can be like other animals, go into another dimension like air, travel in the sky.
Or traveling in the water.
Yeah, or in space.
Well, no animal has done that though.
So
that's true. We're the first animal.
Yeah. I got a question for both of you guys.
But we can mimic an animal the way they move
in space.
I feel like we could.
Because every animal here needs to use leverage.
Yeah.
Against either solid, liquid, or gas. In vacuum, you leverage nothing. You have to propel. And the propellant, how would you imagine a living organism propelling?
By light.
Actually, you gotta watch Hail Mary. You gotta watch Hail Mary. It'll be spoiling if I mention what I'm about to say.
I would have to propel maybe like from how we do it now is we propel from Earth, and that force would just carry us.
Because you need to throw something away, right? Equal opposite reaction, right? You throw something away, that force me throwing it away will also force me back because the normal force, right?
Yeah, and there's not like the gradient motor situation.
Yeah,
where,
that's
like,
no
environmental.
Yeah, there's no environmental.
But there's
assistance.
gravity from other bodies.
So let's say we would design a suit for space, right? Inspired by biomimicry. What upgrade would you put there?
Suit for space.
Let's say you look at can you pull up spacesuits? What like biomimicry edition would you give spacesuits?
I feel like a radiation, or like mushrooms.
Oh, you mean like the fungus that eats the radiation?
Yeah, or like a self-healing that we talked about. If there's a cut and it would heal.
It'll self-seal.
Okay, but that one's not very good because there's no moisture.
Well, some self-sealing. Yeah, well, some self-sealing does not need moisture, right? Remember?
That's true. The vacuum.
Yeah, we shown that, right?
If they have a layer underneath and they
Yeah.
have the metal layer on top of that, then the vacuum would press it together.
Or even the plastic one, just now they showed, right? You just need to push it together. The plastic will already stick.
Yeah, but they would have to touch it, and they might not know where the tear is.
That's true.
There's some type of exoskeleton.
And I would think the gripper from the geckos would probably be useful because you don't have to keep holding on to stuff. You just just hold on to that.
So
we just combine all the deals.
Yeah.
I mean, it'd be better than what they already have.
Yeah.
So let me ask you guys a question.
I don't know what they have already.
So I feel like we accomplished quite a bit with Physics Society this semester. What is the one thing? What would be something you'd want to do next semester after knowing now
how to get funding
and things like that?
I think we'd have to get involved in the community more, because the engineering camps, they have them in the summer, and STEM camps.
Damn, I'm gonna miss that this year. I have to.
And so I think it's important to encourage younger generations, because with the population in countries, it's the same thing with science. Well, I mean, there needs to be a generation that also is encouraged to go into science. So I think since we know how to get funding, we should also do at least something regularly and consistently, same thing, to to encourage younger people. So visiting schools, talking to them, and making it seem less intimidating.
Oh, actually, this is something we three of us need to talk about. But I will, but basically, in the case, because next semester he will be gone. Okay, so
but I still might even be here though.
No, you will be here. But I mean, you won't be a student here, so you can't really run the org.
Yeah.
So my question is, how would you feel if you were to take the role of president? Would you?
Guys.
Would you want to?
I think next semester I have less classes, so workload wise, it would be more manageable. At the same time, communication, I'm a quiet person, so it's hard for me to project my voice in certain situations. In a small group, it's easier. In a larger group, it's harder for me because I don't want to grab people's attention that way. It doesn't come naturally to me unless I have to, for a presentation. And also, I don't know, I like when people are, listening to me. If they're not listening to me, I don't want to project my voice to, have to exert energy to get their attention. I'm a lazy person, I think. So, I'd be motivated to be leader, but I'm just unsure on, keeping people's attention, grabbing it, it's that for me. But I also think I could step into it. The people who stay, who listen, the people I can reach, I would be consistent and reach with them.
Yeah, my what I think we need to get better at
Communication.
is communication and recruiting.
I think recruitment.
And I don't know what that. I don't know if it's because of there isn't much interest in physics. I don't know if it's because we're not doing the right thing. Maybe once we have like an engineering project.
Yeah, I really think it's the engineering projects that will get more people, because people want to see things done. You know, like they want to see, they want to touch it, they want to feel it. You know, if it's just lectures, some students will be interested. Maybe the nerds like us. But to get the general population to start getting interested, you need to get shit done. You need to show them that they can get a chance to do it. That's why I think the cloud chamber is a good start.
Yeah. Yes. And so what do you guys think about this? Because I was thinking about this the other day. So I think. So because I'm gonna basically take over, it seems like, Physics Society over at OU, because it's essentially non-existent over there from what I've seen. And so what do y'all think about us just having one Discord, like for OU and UCO?
I think that'd be pretty cool.
And so we have people from multiple colleges on there. I mean, I know we at the moment we still have a hard time getting people to interact, but I think the more people we get on there, maybe the more interaction that happens.
Yeah, I think there'll be like more people who like physics. You know, just like becomes a broader place to share ideas.
Yeah, and you know, I think also a lot of it is, you know, maybe we do feel kind of new to people, and so they're not really sure about what Physics Society is. Maybe, I don't know. Maybe that goes into the communication thing. I don't know. But, you know, we have a whole summer to think about it, right? Like how we think that we can like move forward with this thing.
Because how we can keep growing and like.
Because the last thing I want to happen is for it to just, you know, fizzle out, right?
Yeah.
But I think we've got a lot of momentum though. And, you know, like Teo told us before last summer, like, let's keep the momentum going, which I feel like we have. So.
Yeah, we definitely have done that.
Yeah. So yeah, let's just let's try to keep in mind, like, you know, these breaks that are especially coming up the whole summer, like gives us a lot of time to get things, get ideas fleshed out. And so that whenever this semester starts, we can hit the ground running, kind of like how we did this semester and the semester before.
Yeah.
But yeah, I'm excited. Yeah.
I mean, if we do projects next semester onwards, would you be here to do the projects? Would you have time for that? Because you're in graduate school.
Yeah,
that's a whole different ballgame.
Yeah, I don't know. We're just gonna have to play it by ear. Yeah, I don't know. And that's the thing, though. It's like, okay, well, you know, maybe we have like a joint college project.
That would be awesome,
right?
Actually, I think so too.
Or maybe we have like a competition of some sort, right? Like a rocket building competition. That's always interested me. It's very tied to Physics Society, space physics, you know. So.
Oh my God, dude. Okay. Before we get into that, let's search up the last thing I want to show. So it's UNSW. Space CubeSat.
Oh. Cube what?
They go on
CubeSat. Cube.
Oh yeah.
You're good.
CubeSat.
SAT.
CubeSat.
Yeah. Images. They have students build these small little satellites to send to space.
Ooh.
At least low Earth orbit.
That'd be cool. That'd be really cool.
They like go onto something that's already going to space, and they like launch it with it.
It's a real project.
Or wait, they launch it. They launch this thing into space, or people drop it into space.
So they make a satellite that they test, they prototype, and they have a specific objective. Obviously, either it's carbon detection, radiation, whatever. It doesn't matter. So the whole point is this cargo is meant to do something in space, and once this project is very, very well developed, right? They'll actually ask. They collaborate with real space programs to send it to space.
That'd be cool. Yeah.
So it's basically an engineering program to develop a satellite.
Okay.
CubeSat is one of the most simplest, quote-unquote, simplest satellites you can make.
So this sort of goes into an idea that we had at the beginning of this semester, right? With our projects, right? We have like a short-term project.
Or like small project.
A long-term project, and then maybe a joint project, right?
I feel like long-term projects should be joint. Because they take years, they take months, and these
and then the resources of two universities collaborate.
Short-term projects, it could be collaborated, is optional. So like a cloud chamber, we don't have to have a collaboration for that.
Yeah, I guess the only thing about that is like all the supplies and who's gonna pay for what, right? Gets a little fuzzy, right? And where you're gonna keep the supplies.
So I think that comes down to how Physics Society is gonna start growing. If we start growing, if we start making projects, and we start having more and more of our own stuff, we need to start looking on campus, requesting for places to store our stuff. Because you Formula SAE, for example, do you know that organization on campus?
They use the makerspace, right?
They use the makerspace to make actual race cars.
Yeah.
To take part in the national Formula SAE competition. We need a proper workspace. Either we collaborate with Makerspace or we collaborate with any of the labs, but we also need our own storage room.
So, and then this is also one thing to think about, right? Is actual competitions to to like go and do, right? Like, so my buddy over at OU, he runs IEEE, and yeah, that's cool. And they went to like a national competition. Competition, yeah. And so, you know, maybe we should even
take part in competitions, hackathons,
to you know, sort of help with, you know, helping students build resume lines, right?
No, that should be the whole point. I feel like that should be the whole point.
And so, you know, so not only building something because we think it's cool, but then trying to tie it into some type of maybe local competition that's going on, or a national thing.
Or competition.
And then so that's one thing we could go and ask for money for. Like, hey, we have this big competition that we're wanting to enter, and we need money for it, right? So.
Yeah, I think that should be definitely a goal.
Yeah.
I don't know about next semester, but definitely like next year. I feel like we could do that because they had that Rusty in the Discord talked about that competition, and it was physics, but I forgot the exact like.
And I even wonder, like, you know, there's like those makeathons.
Yeah, makeathons.
I wonder if Physics Society
can partake in that. Yeah,
like I wonder if Physics Society can have a team, or if I wonder if it's just limited to universities.
No, we can have our own team.
Okay.
You just need to form a team to represent UCO to go.
Okay, that would be interesting.
And then yeah, because a lot of, for example, a lot of students, they go under the guise of their institute of UCO to.
Because I heard that UCOSA, or I think you were telling me this, right? That UCOSA has like $100,000 a semester or something like that.
More than that.
Yeah.
But to be fair, they are funding over 300 organizations on campus.
Yeah. But you know, I think
they also fund their own.
I think that's why we need to think of these things during the breaks, so that once the semester hits, we can
hit the ground running.
We can be the first to the bank.
Yeah.
You know.
So it's easier to get at the beginning. It's also easier to get towards the end. In the middle is the hardest part to get.
Yeah,
because towards the end they try to use it up.
Well, yeah, because the middle
they have a lot to give.
is when a lot of these clubs are finally starting to get momentum.
Yes.
Whereas if we have the momentum early,
and also because early they are more willing to give, they have more to give.
Yeah. Yeah.
So and the demand starts rising towards the middle, like what you said.
Yeah.
So competition will rise towards the middle. And anyways, so before we finally end it, I just want to ask, like, aside from the cloud chamber, of course we have a list of ideas, and now maybe CubeSat, or a simpler version of CubeSat. Maybe we make a Sputnik, like there's just a simple radio satellite. So what else do you guys think we should have as projects that, because CubeSat is too complicated, it's definitely a multi-semester project. What about you guys? What do you think should be a project for Physics Society? Because again, the cloud chamber, the reason why we're budgeting for 10, right, 650, is because we can make multiple. Some of them we bring to demonstrations, and of course a lot of them we actually plan to merge it to make a bigger one.
I think what we need to do, right, we need to get sort of the idea down on paper, right, or we can maybe put this in Notion, right, of like what are the, because I feel like the project should have like a theme, right? So one theme would be like competition, and then the other theme is like short term, long term, and then another theme would be demos for community outreach.
Yeah.
So
different categories.
Yeah. So that's my thought. And like short term, maybe we have something that's like
electromagnet.
Maybe
like a coil, and then we give it charge.
Yeah,
magnetism and electrical.
Yeah, exactly. It's maybe more based on it's more of a representation of physics instead of like an engineering type project, right? Yeah. It's more like we're building this thing to understand physics, right? Whereas one of an engineering project is something to build using physics, right? And engineering principles. And then, I think we need to get involved in competitions. And
I think the pendulum to like show the chaos theory, that would be cool.
Yeah.
That would be pretty doable.
So, like, would we just categorize short term is something we can do in a semester, long term is multi-semester, and then we have also immediate projects, things we can do in less than a week.
I have some immediate ones.
Immediate ones? I mean, Cloud Chamber, for example, is immediate.
It's
you can just put it together.
Physics one, actually. These are the ones I had this past semester. It was a rocking chair, and it was supposed to be for Halloween. Which I had the rocking chair. I had the stuff. Just didn't do it because I wanted to make sure it worked before we did it for the club. But yeah.
Yeah, it could be like
motor powered rocking.
Yeah, along those lines of like
3D printed
how
rockets.
physics, sort of like how Physics Society can give back to UCO, right? Or to stay involved in things going around at UCO, right? Because there's always like events that the engineering department is putting on, or UCO, the college is putting on, right? And so we could come up with engineering projects like that to
recruit people too, like like they make some cool decorations.
Yeah, and when we do like tabling sessions, right, and fundraising type stuff, we should have some physics/engineering things on hand that we can take with us to sort of like show, hey, these are the types of things we do, right?
Yeah.
So, yeah, I mean, I know it sounds like a lot, but at the same time, I think the different things will grab different people, right? So
you say that again. We'll have pure physics ones. Some of them is engineering ones, and some is more like a demo for physics concept, and some is more like problem solving.
Yeah, and some specific to certain events that happen at UCO, right? Right, like, you know, if we have like a closet space where we can put stuff, right? We could, you know, we could pull out the chair thing every Halloween or whatever, right? So we don't have to get rid of things, right? We could have just things that are like based off of the certain time of year. Yeah.
Projects that we made, like for ECO. Another one I had was like motion sensing dropping. It was an Arduino like motion detector, and it would drop a spider. I mean, I have this stuff for it. I just have not had the time.
Or, you know, like here in the library and in other other buildings, right? There's those glass cabinets, right, that will have like a sort of a memorial, or I think that's what you would call it, of certain things, right? Like, so we could have one of like, you know, we've talked about having like a podcast over giants, right? We could have a memorial to like the giants of physics, right? So, and possibly maybe even the UCO library has certain artifacts that we could put in display.
That would be cool.
There, right? So, and
that would be a long-term collaboration thing.
Yeah,
that'd be cool.
Or we like remake some of the devices or like instruments in physics, like if we made a cathode ray tube.
Yeah.
We'd put it in display and then bring it out when we show people.
That'll be dope.
Yeah. Anyways, guys, let's wrap this thing up.
Yep, let's wrap it up.
All right. Well, until
next time.
Until next time.
Well, we don't need to clap. Okay.